Hello everyone, welcome to the day 7 of the LLM Mastery course. In this video, I'm going to show you all how you can pre-train your own LLM from ground up with the help of this Zero to Hero LLM pre-training guide. This guide is all you need for you to pre-train your LLM today itself. Yes, you heard it right. You can pre-train your own LLM today with the help of this guide, even if you are an enterprise or an individual, doesn't matter. Let's start with the video now. In pre-training an LLM, the most important part is creating a training pipeline. Rather than coding it, framing a pipeline which is very scalable and also efficient enough for your model to perform well is very important so that your LLM becomes very robust. Let's see how a training pipeline should be constructed for pre-training any custom LLM. Any pre-training of LLM will contain 5 stages, starting with data collection, data processing, training LLM, LLM evaluation, fine tuning LLM. We'll be seeing these sections in detail where what you need to do in each of this section. Let's start with data collection. What is data collection? Data collection is the process of gathering large volumes of diverse text data. With pre-training, this definition can't be like more apt. This is the most apt definition when you come to data collection for pre-training because two keywords are very important. You need large volumes of data and also it should be very diverse in nature because that is when your LLM will understand what is the language and what are the semantics involved in the language, how it varies syntactically. Everything is understood only when you provide diverse variety of large volumes of data. So what is the importance of this? Like I said, this will form the foundation of your language model. So if the foundation is not good, you're not able to adapt for any of your use case. So this is going to form the foundation for your LLM. What is the goal of the stage? It is to acquire a broad range of human knowledge sample data. So the data should represent a broad human knowledge and also how to use a language. Okay, it should contain more about knowledge. Also say like how to construct a language. What are the sources in which you can collect a pre-training data? First, you can crawl it from the websites by using common crawl libraries, or you can also use custom web scraping. You can take books datasets uh, from Gutenberg library, or also you can go for Google Books. There are some other options as well which you can check it out. In open source dataset hubs like Hugging Face and Kaggle, you'll have a wide variety of data. Those can be considered as well. And if you are going for news kind of a data so that your LLM gets updated with current affairs, you can go for news APIs and blogs. And when you go for domain related, for example, what if I want to pre-train my own legal LLM? Okay, so I need to first find legal documents. There are lots of documents like government reports, SEC filings. There are lots of reports like that which you can cover for your legal LLM. And when you go for a scientific kind of an LLM, you can obviously go for Archive. Archive is open source. And then you have PubMed as a big source for medical domain. Now, what are the things you need to consider when you are collecting your data? First, volume must be in terabytes. Usually it will be in terabytes if you collect how it is supposed to be collected. So here there are two challenges. First, you need to collect terabytes of text data. That is one. You need to process terabytes of text data. That is two. And then you need to store terabytes of text data. That is three. Okay, all of these are something you need to consider and make an infrastructure such that it can handle this volume. Next, like I said, large volumes of diverse data. So that becomes your next consideration. Make sure that your data is having wide variety of domains and dialects. And if you are training multilingual model, so it should contain multiple languages. And even in multiple languages, it should cover a wide variety of domains and dialects. That is important. Okay. And then next we have the quality. So when you are providing data, like I said, this is going to form the foundation of your LLM. So make sure that the quality is very high by removing the low quality spam content from your pre-training data set, or even if you collect it from any data source, we won't know, right? The reliability of those data set is always in question. So make sure that that is considered. And if you are working with some organization, then lot of ethical considerations will come into the picture. Like, for example, you need to see the license of the data set, and commonly you need to see the privacy. uh, it is a very important ethical consideration. Make sure that no private informations are went, for example, personal user information, and so on and so forth. And also, when you go for website data, there will be always a lot of bias inside that. If you see in real world, in internet itself, there are lots of bias which is shown in any blogs if you search for. Okay, for example, if you search a content, everyone is giving their perspective, which means there is an indirect bias induced into it. So make sure that those bias are reduced as much as possible. So what are the challenges here? When you're considering these, like I said, first, storage and processing becomes a big challenge. And then when you have multiple data sources, there is a high possibility that your data might be available in multiple sources, same data in multiple sources. So you need to write a complex logic to remove all those duplicates. And then write a processing pipeline which will handle like different file formats, regardless of how complex it is. HTML, PDF, text, CSV, it doesn't matter what kind of a file format it is. And then file encoding. So there are possibilities. For example, if you go to ChatGPT, it can generate emojis, right? So those it are able to generate because it is UTF-8 encoded. So if you want your model also to do that, so you need to make sure that you can process UTF-8 encoded file format data and all. And then you have ASCII file format as well. That is another format. Next, very important thing is datasets with updated information. If you want your LLM to be relevant to the situation which is there in the current world, you need to ensure that it is updated with a lot of information. So that is why if you see any big organization will say this is their cutoff date. The more recent the cutoff date, the better it will be adapted to current world scenario. And legal and ethics. So you need to make sure that you abide by the copyright laws, and also make sure that the personal information is anonymized so that you will use it for fair. Next, you know how you can collect the data, you know the challenges involved in it. But like I said, there are lots of processing which is required. That is what we discussed here, right? Deduplication. Deduplication is one of the processing methods, but there are many other processing because your data source is not always reliable. So the next session is about data pre-processing. How will you process your data? So first, what is data pre-processing? Transforming a raw text data into a clean, structured format which is suitable for model training is known as data pre-processing. Again, a short, very descriptive and self-explanatory definition, followed by which you have the importance of the stage. I don't think we need to emphasize a lot on this important stage, because how much ever we create a very complex architecture with whatever state of the art technology it is there at that time, if you don't have a good data, you're not going to get good model, right? So imagine you are a very intelligent guy, or like, you are an intelligent person, and your teacher is teaching you something wrong. Okay, you are so intelligent, so you'll know, okay, like this is the teacher's guideline, so for me that is correct. Okay, if I ask you something about that, you'll be able to answer it because you're intelligent, you can remember a lot, you will answer me correctly according to your teacher. But you are fed wrong information, which means you're saying something wrong with high confidence. That is not a mistake of you, it's a mistake of your teacher, right? So similarly, if you give wrong data or low quality data to the LLM, it is not the mistake of the LLM to say wrong, it's a mistake of the person who is creating that, right? So make sure that the data is quality ensured. Okay, so that is the most important uh, aspect of data pre-processing. Along with that, you need to ensure consistency and relevancy. Your data should be consistent with your use case in which you want to train it for. For example, if I want to train it for a legal domain and if I'm training it for a medical domain, it doesn't make any sense, right? And let's say you're instruction tuning it on medical domain, but you pre-trained it with general domain. How it will be able to adapt to the small terms, which is not something it would have seen in the pre-training stage, right? So to maintain that consistency, a simple format, for example, one might be HTML, one might be an XML, one might be a normal text. If you're giving different formats, your LLM will be confused what to do, right? So those are the things which are coming under consistency and relevancy. Like I said, you need to make sure that your model is relevant, right, to any scenario. So those are the importance of this stage. What are your goals? First, removing noise and irrelevant information. If that is irrelevant, you'll just remove it, and if it is a noise, you'll remove it. Like I said, if that is not something related to your use case, just remove it. Again, that is one example of relevance and consistency. There are lots of other examples. I'm just saying a domain specific nature because if you're going for a general pre-training, right? Maybe if you want to do a learning out of it, you can pre-train your own LLM. But most of the pre-training of LLM will be happening only if you want a custom domain pre-training. So I'm more emphasizing on custom domain. Okay. Probably, in upcoming days, we'll custom pre-train our own LLM for a custom domain of our choice, right? So let's see how that is done as well. Probably something like a financial domain or legal domain or healthcare. We'll try to do that. Maybe you can put it in the comment section on which domain you want the video to be. Okay. So that is the first goal. Second, standardized text format. This is to ensure the consistency, right? So if you have a standardized text format, it means your data is consistent among its samples. And then next, you have preparing data which is efficient for uh, processing by the model. So this ensures that your model has high data quality and it is very much processable by your model. So in data processing, one of the most important step is text cleaning. Okay. In text cleaning, there are lots of steps which you can do. For example, removing HTML tags, removing stop words, handling special characters, either removing it or encoding it in some different format. And then you have standardization of text, and then deduplication of content. All of these fall under text cleaning, and these are simple steps, right? You can just do like each one of these can be done with the help of regex. Probably not deduplication. Deduplication is something you need to do with some complex logic. If you do a simple regex, it won't work, but others can be done with a simple regex itself. Now, the next thing is vocabulary creation. Vocabulary is something like your model's knowledge to some extent can be understood with the help of the vocabulary, right? It is like if I ask you what are the words you know, you list out your words, right? The more you know, the better you can express what you know. That is the idea of any language, right? The language is there to convey your knowledge. So, more the words you have, better you'll be able to express what you know. That can be understood by vocabulary. So, vocabulary creation almost becomes a very crucial stage here. What is vocabulary creation? First, it is a process of compiling unique tokens from the dataset. So whatever dataset you have, you'll take all those unique tokens and that becomes your vocabulary. Here you need to determine your vocabulary size first. Okay. And for example, only I can remember only 25,000 words, right? Uh, I'm speaking in Indian English here. So if someone like an American is speaking, you'll be able to understand that it is an American who is speaking here. There are two reasons for that. One is the accent of the person. That is one thing. And the another one is the way they use their words. It will be very much different than how an Indian will use his words, right? So vocabulary shows a lot of things. And here, what differentiates it, their vocabulary is different, my vocabulary is different. I can speak Tamil, I can speak English, I can speak Hindi to a bit, which means my vocabulary is this much. Okay. So if I'm going to learn new words, I'll forget some of my old words, right? So determining that vocabulary size is very important. How much words I can remember efficiently. So common vocabulary size now it has become around 128K, but it differs um, among the LLMs and what the use case demands. So, for example, if it is a legal domain or a medical domain, you need to make sure that those technical terms are there as a single token, right? That will reduce the complexity of the LLM to generate tokens correctly and also understand a sequence of tokens correctly. For example, if it is pneumonia in medical domain, if you're having new as one token and then monia as another token, maybe mon and then ia, three tokens, right? Three tokens, understanding three tokens in a sequence is harder than understanding a single token. So make sure that your vocabulary has, you know, the correct number of tokens, because that is going to determine the knowledge of the LLM. And then handling out of vocabulary words is very important. So for this, there are special tokens. First, padding. You need to add those tokens. Padding is used for padding sequences to a fixed length, because LLMs can be trained only with a fixed length across the batch size. So if there is a length mismatch, you need to add pad tokens. And then you have UNK tokens, which is used to represent unknown and rare words. And then we have the CLS token, which is often used to as a special classification token. Basically, this token will have an overall information about the whole sequence. And then SEP token, which is to separate different parts of the input. For example, I want to separate that. This is a paragraph, and then this is the next paragraph, to show that we'll have a separator token. Next, we have another important stage, which is tokenization. We have already made a detailed video on different types of tokenization which you can do. So if you haven't checked that video, please make sure that you have checked it, because this is a very important stage, because you need to create your own tokenizer. Vocabulary creation also comes under tokenization, because based on your vocabulary only tokenization will happen. Okay, so make sure that you watch that video. The links will be in the description. So what is tokenization? Tokenization is the process of breaking the text into smaller units, and this smaller units is known as tokens. What are the types of tokenization which are there? Word based, subword based, and then character based. These are the most three common formats of tokenization. So while you're creating your tokenizer, what you'll do is first you'll take the data, you'll train it on your domain, and then you'll reduce the number of words to your vocabulary. And then what you will do is you will pre-tokenize your sentence. Okay, so it can involve normalization, reducing the sequence length, or so on and so forth. Once that is done, you will perform your splits, and then your vocabulary will be created. Okay, and based on this vocabulary you will tokenize your data set at runtime and also at training. Okay, so I hope you understood why vocabulary creation and tokenization are together. So, what is the importance of tokenization in the model performance? First, it will balance the vocabulary size with the token's informativeness. Like I said, if it is a domain specific one, right, you need to make sure that your vocabulary covers, like, the token informativeness correctly. If there is a technical term, make sure that those are single tokens as much as possible, or even at two tokens. Okay. So, and then we have another important step, reason, which is to handle out of vocabulary tokens. So, there are lots of ways you can handle out of vocabulary words, and one of those ways is to use byte pair encoding method. Again, if you haven't watched the video, please watch it, because I've shown how byte pair encoding works theoretically, and also I've shown it programmatically. Okay, so please make sure that you have watched that video once you complete this video. Next, you need to implement your tokenizers. First, either you can use pre-trained tokenizers, which are there in Hugging Face, NLTK, Spacey, depends on your use case. So if you're going for word-based or character-based, you have your options in Spacey and NLTK. But if you're going for subword kind of advanced tokenizers, you have your options in Hugging Face. Or you can use your own custom tokenizer, that is more than fine. Next, it is to encode your input at runtime, because you are now created your tokenizer. You need to use this to encode your input at real time. So what is this step all about? It is about creating your tokens into numerical IDs. So you will have your vocabulary. In your vocabulary, each token will have a number to it, a numerical ID, so to speak, which will be commonly termed as input ID. Okay. And so basically it is to create the input IDs for your tokens. And then once that is done, you'll create the input sequence for the model itself, where raw text will be converted into sequences of tokens IDs. And then what you'll do is you'll handle the variable length inputs. So like I said, an LLM needs every sequence to be of the same length in the batch. Okay. Across batches, it is not important. But inside the batch, you need to have every input to be at the same length. So if it is lesser than the length you want, so it should be padded. So if it is greater than the length you want, it should be truncated. And if you do padding, you need to make sure the attention masks are there, because that is the one which will say, like, you have padded these tokens. So that becomes very important. So when you're handling variable length inputs, these will come into the picture. And then next is to implement efficient encoding pipelines. When you're having a large number of data for training, it is very important that you parallelize this encoding process, because when you're pre-training it, the encoding process happens in CPU. So you need to make sure that that is fast enough and it doesn't slow your pre-training pipeline. Okay. And then another thing is, when you have large number of data sets, like I said, you're using CPU and RAM, you need to make sure that this process is optimized for memory, which is RAM, and then processing speed, how to use the CPU efficiently. So these are, like, runtime tokenization step, or which is known as encoding input stage. What are the ways you can augment your data? Because like I said, diversity is very important, right? So how we can create that diversity? That stage is named as data augmentation. First, what you can do is you can do synonym replacement. So for that, you can use something like word nets or word embeddings to find the words which are closer to it, which replace those words but doesn't change the semantic meaning. Okay, semantically both are same, but the words are different, so that the model will understand, okay, it is not like I should always use the one word there. I can also use another word to show that. Okay. And then there is another stage known as back translation. Most of these data augmentation are for increasing the amount of data and make it more diverse. Okay. So for example, you have uh, data. What you can do is you can translate to another language. For example, I have something in English. I can translate it to Tamil and then back translate it into English. So depends on the knowledge of LLM or whatever model I have for translation, it will try to translate it in a different way. Okay, same meaning is conveyed in a different sequence, but both are right, right? So in this case, you have two data, which means you're increasing the volume of data and you're increasing the diversity of the data as well. And then next comes random insertion or deletion. So this step is known as, like, noising or denoising kind of stage, where what you will do is you'll just insert random words from the vocabulary, insert into your dataset. Okay, so it shouldn't make any sense, because in real time when you work, you don't explain your things correctly, right? For example, if you give to ChatGPT with some spelling mistakes or even some filler words, it is able to understand it because it is trained in a robust manner that it can handle those kind of sequences as well. Okay, that is what is going to shape your different writing styles. Like I said, Indians will have a lot of fillers in it, and their English will be very simple. But an Australian English is something very different than an Indian English, which is very, very different than an American English, because they'll be more eloquent, right? So to simulate these different writing styles, you can just randomly insert and delete some words from the vocabulary. But make sure that you do it correctly, because if you do something wrong, your LLM is going to be like, I'm not able to understand what you're trying to say here, something like that. Now, what are the importance for you to do the data augmentation? You need to increase your data size and diversity. That is one, like I said already. And then when you do these two, your model, like I said, it will be able to handle various inputs. So it is becoming more robust. And since you have a variety, it prevents overfitting as well. And here I left a point for generation. You can also use bigger LLMs. Okay. So for example, proprietary APIs like ChatGPT or Claude, make sure that you follow their licenses. That is there, but those can be used as well. Now we are completed with the main stage, which is data related. Data collection and data processing are done. The next stage is to train your LLM. The first stage in training the LLM is designing your architecture. So, what can you do to design an LLM architecture? For you to know that, you need to first understand the evolution of your language model architecture. First, it was just n-gram model. Just predict the next gram, like two words. It will just try to understand and predict the next two words, something like that. Then it came with the neural network architecture, and then came transformer architecture in 2017, and the world is now revolutionized with LLMs like Llama 2, Mistral, and then Llama 3. There are a lot of things lately. Lately, there was a model released known as Ministral, something like that. There are lots of models which are released on these lines, right? These are the ways the architectures are revolutionized. So you need to make sure that you follow the evolution as well and adapt your LLM to those evolutions. So the design goals. So whatever goals these LLMs had to revolutionize the architectures and revolutionize the worlds again is, first it needs to capture the long range dependencies, which is nothing but the context length. Longer the context length, better it can remember a lot of things for a longer time, right? So that is very important. Second, it should be scalable. Okay, it should be scalable for billions of parameters. The architecture should be scalable for billion parameters. What does it mean here? You see, when you're training your LLM, right, make sure that you know why transformers were released. Transformers were released because it has this parallelization capability. Okay, without parallelization, if you're going to make it everything sequential, it is not going to be easy for you to train a billion parameters. Okay, make sure that your architecture is scalable in that way. For example, if you go through codes of Facebook, right, they would have used something known as row parallel linear, column parallel linear. So they would have done a lot of parallelization. They would have emphasized on that. That is why they are one of the market leaders, right? And also, your model should be able to process large amounts of data. So what does that mean? So if you are having a large amount of data, right, your model should be able to remember that much. So the approximate size that might involve the approximate sizing of your number of layers, the embedding dimension. A lot of things will come under finding the efficient processing of large amounts of data. So as an overview, for transformer architecture, it contains embeddings layers, which will convert token IDs into dense vector representations, which is nothing but embeddings. Positional encoding, which will provide the sequence order information saying like this token comes after this token. And then you have multi-head attention mechanism, which will allow you to focus on different parts of the input. And then you have feed forward, which will process the attention output, combine the information which was obtained from multiple attention hits together. And then finally layer normalization, which is to stabilize the training process. So I'm just giving an overview here because I've made two detailed videos on transformer architecture. One was to make you understand how transformers work, and then another one is to implement that transformers from scratch, line by line, where I would have shown the math equation and then I would have converted into code. So if you haven't checked those two videos as well, please make sure that you check those two videos. For all the videos, the playlist link is in the description. So lately there have been a lot of architectural advancements. So here are some of those. The main components in feed forward network, in your transformers are positional encoding, attention, and feed forward, right? In all of these components, there have been, let's say, huge number of advancements to increase the performance and the efficiency of the architecture. What does the efficiency of the architecture mean? It is about uh, the latency and the memory consumption when it comes to the efficiency, and performance means the accuracy. Okay, so here the positional encoding for positional encoding, there are varieties of positional encoding, and some of those important types are absolute encoding, in which there are types like sinusoidal, binary, algebraic, and then relative. You have transformer Excel method, Shaw et al. Method, and so on and so forth in there. And in those relative encoding methods, there have been a huge number of advancements because with relative encoding only, you'll be able to handle a long range dependency of text. Right. So for those came rope and alibi, two of the most commonly used and most advanced methods. And then to bridge the gap between absolute and relative, there is mixture portion encoding as well. Don't worry about these types. If you don't know about these types, no worries. Again, the video links are in the description. Please make sure that you watch those. Whatever I speak about architectural advancements now, for all of those architectural advancements, I've explained it in detail in the previous days. Okay? So make sure that you watch that. Same goes for attention. Multi-head, multi-query, multi-group query. So multi-query and group query came for increasing the efficiency of the architecture, and sliding window and descent angle came for increasing the performance of the architecture. Okay. In feed forward, directly there is not a lot of optimization because feed forward is just linear layers. But feed forward consists of activation functions, and lately there have been a lot of work around activation functions. There is a family of activation function which came recently that known as glue activation functions. There is jglue and swiglue, which is common, which are just glue versions of Jelu and Swish. Okay, so you can also use Jelu and Swish. Those are very common. But if you want, you can also try with Jeglu and Swiglue. The second thing is using those feed forward as MOE. Okay, this is something very common right now. If you have multiple languages to handle those, people go for a mixture of export kind of an approach. That can be done as well. All right. Choice of advancement can be customized as per your requirement. If you want it to be more on the performance side, you will go for a more aggressive approach. And if you want it to be the more on the efficient side, you'll be more focused on, like, reducing the complexity of the architecture, reducing the memory consumption, and so on and so forth. Make sure that you select the appropriate components. Next comes the model scaling. Now you have a basic architecture. You need to scale the model, right? In that, the first parameter is to increasing the model size. Large language model. The name suggests that it should be large, right? So, what are you going to do to increase the model size? First thing is to add more layers to increase the depth. Why you need to do that? Whenever you do something, make sure that you ask the question why, what, when, how. If there is an answer possible for all the questions, and in these kind of questions, as steps, right? You need to ask why you need to do that first. Why you need to do adding of more layers to increase the depth. I can just increase the embedding dimension, it would have been uh, bigger, right? Why you need to increase the depth? It is to increase the reasoning level. The more deep it goes, it can drill down to different nuances to the minute bit. Okay, so that is why you need to increase the depth. If you see the architectures which are very good with reasoning, right, they'll have a very deep network. So even with small parameters, people are now using 20 to 25 layers. Why is it important to have that much layers? Because the more down you go, you'll go to the minute details. Okay. But it is also important that you increase the embedding size or the hidden size, because with increasing of the embedding or hidden size, you'll capture more information. You'll remember more information. All right. So that becomes a very important step as well. So you need to find a trade-off between these two. Like, I have an optimal number of, let's say, 3 billion parameters. I need to find an optimal number of layers and the hidden size of it. Okay. These are under the consideration that you want to create your own architecture. If you're referring someone's architecture, they have been already optimized. So you need not do a lot of things there. But if you want to do something by yourself, these are some things you need to consider. And then next is to make sure that the trade-offs are correct between the model size and the computational requirements, because with the increase in the model size, your trade-offs are going to be high because the computation requirements are always going to be a bottleneck, right? So make sure that those trade-offs are correctly managed. And then we have efficient scaling techniques. So don't worry if you are just, like, confused how I can make sure that these trade-offs are efficiently done, because we are going to pre-train our own LLM very soon. So once we do that, you will understand as a code part how I'll do that, something like that. Okay. Next, efficient scaling techniques. When you have a large number of parameters, you need to make sure that your model is scalable, right? What are the things you can do for that? First, add sparse attention mechanisms. If you go for a dense method, always it is going to be more complex to compute. So you can go for a sparse attention mechanism. and then you can share your parameters across layers. And also, like I said, MOE is a very good method because at runtime, only the limited number of experts is going to be loaded in the memory. Now, this is how you need to design your architecture. You have your scaling part completed. You need what are the architectural advancements you need to include in your pipeline based on your requirement. All of those are done, right? You're making it scalable. Next, what you need to train this model, right? That is what we are going to see now. So, introduction to LLM training. So here we are focusing on pre-training because pre-training is the process of teaching the model to understand and generate language. That is the main idea of pre-training. Okay, any task you do in pre-training, the aim of this task should be to understand and generate language slash domain, because there are lots of scenarios where you will pre-train it just for the domain. Okay, so for example, I want to pre-train it for medical domain, something like that. So it is to either pre-train to understand and generate tokens related to the domain or the language. What is the importance of this step? This is the core step in creating a versatile language model. ChatGPT is very versatile, right? How it is possible? Because they covered wide range of domain, wide range of languages, everything, wide range of dialects, and so on and so forth. And they trained it on top of those versatile data set, right? So that is why, again, if you see, I'm talking about training and emphasizing on data set. So that is why data processing section had that much emphasis by having more number of time dedicated to it. So what is the goal of pre-training here? It is to develop a model which has a broad language understanding, and you need to enable zero shot and few shot learning capabilities. So if you, for example, if you give to ChatGPT, if ChatGPT doesn't know something, right? Even if it is not in the training data set, it will be able to answer your question. Even if it is not able to answer it directly, if you give some references to it, it will be able to generalize itself. So that is what is enabling zero shot and few shot learning capabilities. Next is to achieve good performance across various NLP tasks. In NLP, there are tasks like, for example, you can put something like summarization, translation, question answering, and so on and so forth as tasks. You need to be adaptable for all those tasks. All right. So that is very important. What are the tasks in which you can pre-train on? First, there is mask language modeling, where you'll randomly mask tokens in your input, and the model will be trained to predict those tokens. Next is to predict the sequence. So here the model will predict which is the sequence which will follow one another. So by this, it will have a sentence level understanding. With mask language modeling, it will have a word level understanding or token level understanding for that matter. And then there is causal language modeling, where what it will do is it will just try to predict the next token based on the previous token. So now mask language model also is about predicting random tokens, and here it is about next token. That is the difference. In mask language modeling, you will use it for encoder models. Okay. So what the task is that the LLM will be expected to understand and say what is the token based on the tokens before and after the mask token. So that can be used with architectures like BERT, T5, and so on and so forth. But causal language modeling is about ensuring that your LLM can say what is the next best token based on the previous token. Okay. Now let's see about causal language modeling in detail, because that is the task in which we'll pre-train our own LLM. What is causal language modeling? But causal language modeling is a task where the model predicts the next token in a sequence using the preceding tokens. So whatever tokens are there before it, those are the cause. See, that is what is the good thing about technical terms. Mostly it will be self-explanatory, so to speak. Causal language modeling. Based on the cause, your language model will say the next token. All right. Example, the sky is. If I say the sky is red, most of you would have say like the sky is blue, the sky is beautiful, something like that. All of you say that because the sky is a common sentence. But if in future I would have said something like the sky is blue, but with some cloud covering, mask cloud covering. Okay. Now you'll say like black, right? How, why it is that? But with some. If I just left it without cloud covering, you would say something else. So if you give a context to what is the future, it becomes mask language modeling, which is an easier task to do because it has the context of what it needs to generate, and then it will generate accordingly, or predict rather. Here it is to generate, right? So it is a bit harder. Next, why is this task important? This is the task which is core to many NLP tasks, and almost any task can be bottled down to a autoregressive task. Some of the most common tasks in NLP, which can be done with the help of causal language modeling, are normal text generation. You can make chatbots, you can make auto completions, and so on and so forth. Why you need to do this? Like I said, this is core to many NLP tasks. That is one, and it will also enable your model to learn the structure, grammar, and context. Because if you are speaking a language, right, you'll say it in a sequence. You'll not think it forward and then answer it, right? You won't do that. You think it and then you'll just deliver it. So your understanding of language as a structure, as a grammar, as a context is like a decoder model which will work on a causal language modeling task, not like an encoder model. Okay. So how does this work? Like I said, it is an autoregressive process. So it will predict tokens one by one. So here in this task, we'll train the model to minimize the cross entropy loss. The cross entropy loss will say how much your model is differing from predicting the best token at a given timestamp. Okay, because if you see language modeling, if you see, it is just classification at the final layer. Okay, it will try to classify what is the next token. Okay, here we'll use only past tokens. Like I said, that is what it makes it autoregressive. And applications, it can be text generation, you can use it with auto completion, and so on and so forth. But the challenge is, like I said, it is a more harder task because it has limited context, and when you speak only the past, there is an inbuilt uh, bias to it. Okay, if you don't explain why you are saying one thing in the future, you are going to be biased to it, right? So there is an inbuilt bias as well. Now, with training of the LLM, right? In a training loop, it is not just that you'll have your LLM, you'll have other things like loss functions, optimizers, your learning rate schedulers, everything will be there. You need to make sure that you have initialized all of those correctly. So the first thing is cross entropy loss. For loss, we'll use cross entropy loss because that is a standard loss function for classification tasks. And here, it is just that your model is going to predict or classify the next token based on the previous token. Okay, so that becomes the standard loss for your causal language modeling training. And here, this will be applied for token wise in language modeling. Okay, so at each token, you'll try to apply this, and that is very important. Okay, and then next you have optimization algorithm. Optimization algorithm is responsible for the backpropagation and updation of weights. And here there are two options. Either you can use Adam, which is a normal optimizer, or a variant of it with the weight decay, and that is Adam W. And for learning rate scheduling, which is to change the learning rate schedule, learning rate in the future. For example, even if you are learning, right, at initial stages, you learn it faster. But going forward, you learn it slower because you know a lot of things. So you need take time to understand those complex concepts slowly. And for that, you'll have a learning rate slower, right? So that is done with the help of the learning rate scheduling method. And for that, you need to choose your warm up period, which will gradually increase across time. And then you have your decay strategies as well, which will basically reduce your learning rates. Okay, linear, cosine, step decay. There are a lot of methods for that. As far as the training process is concerned, um, this is how a simple PyTorch training loop will look like. First, you will pass the data through the model for a number of epochs, and then you will pass that data through the model, which will perform the forward function. Forward function is to just uh, get the model output, and based on the model output, which is known as logits, you will calculate the loss values. You will make sure that the optimizer gradients are zero, and then you will perform your back propagation. Once that is done, you'll step the optimizer, which will update the model parameters based on the gradients you calculated with the loss dot backward, and then the process will repeat. This is how a typical PyTorch training loop will look like for any training processes. Even if it is an LLM or not, doesn't matter. The process remains the same. And for LLM also, the training loop remains the same. Now, for the training process details in detail, right? We already saw the training loop in simple. What happens? The first step is to batching and input preparation. So for this, you'll use dataset and data loader. Okay. So the dataset and data loader is basically used to create mini batches of sequences which are processed, tokenized, and so on and so forth. Which is applied with padding mask, attention mask, everything, like, everything is done and it is ready for model. Next, you're coming on to the forward pass, where you will send the model send the data which you created by batching, and then you'll send it to the model, right? That is forward pass. You'll get the model predictions, which are log hits, and then you'll calculate the loss with the help of it, comparing it to the ground truth. And what you'll do is you will aggregate the loss across the batch. So for a batch, let's say you have 10 sequences. For 10 sequences together, you'll have a loss. And then your back propagation will start, where you will compute gradients for the loss with respect to the model parameters. And for this, you can use automatic differentiation frameworks like PyTorch and TensorFlow. So PyTorch and TensorFlow, they by default have that automatic differentiation running behind. That is what it makes them a good deep learning framework, right? Because the backpropagation is one of the most important aspects of deep learning, and here this makes them a very good framework for deep learning. Next, we have parameter update, where your backpropagation is done, your gradients are calculated. Now you're ready to update your model parameters, which is nothing but the weights and biases, so that your loss is ready. Here, what you'll do is you'll implement a gradient clipping as well, so that you can prevent exploding gradient issues. Now we are coming on to the some real stuffs. Those training loop we discussed till now, it is very common, right? But with pre-training, you have a thing which is very high computation. Okay, so you have a lot of bottleneck to it. There comes the distributed training strategies. You will train it in a distributed manner with a lot of GPUs being involved in there. Okay, so for example, if I'm not wrong, 32,000 GPUs were used for Llama 3 training, if I'm not wrong, 32,000 HN5. Okay, so the hardware requirements are very high. So you need high performance GPUs or TPUs, and also you need fast interconnective network bands for your distributed training, because the data will be distributed through these networks. So there are methods at behind in Torch and all, there is NVLink and all. Okay, and there is InfiniBand, and that is another option. And you also require a large amount of RAM and fast storage, because let me tell you how DDP works in simple. So DDP is a method where you will create instances of your LLM across GPUs, and you will create instances of your datasets across GPUs again, right? So across GPUs, now your data is shared, right? When you have 10 data tokenized together, you're using the same CPU. Okay, so it will consume a large amount of RAM, large amount of storage, and so on and so forth. So your hardware requirements are going to be so high. Next, coming on to the software stack. What is the stack you are going to use for your training? First, you need to choose your deep learning framework. What is the deep learning framework in which you're going to train your LLM on? So like I said, there is options like PyTorch, TensorFlow, PyTorch being my favorite. You can also go for TensorFlow, that is completely your wish. Next comes an important library in your stack, which is distributed training library. What are the things you're going to use for your distributed training? There is TorchRun, which is a default distributed training library of PyTorch. But my favorite is DeepSpeed, because DeepSpeed handles a lot of things. Like, for example, if your memory is not enough, they'll do something like CPU offloading and all, making sure that your model is fitting in those consumer grade limited GPUs. That is why I said we'll pre-train your LLM regardless of what is your GPU, because we are going to try to pre-train an LLM in Colab, Google Colab. Okay, we'll write the code in VS Code, but we'll train it in Google Colab. Um, Next, these are going to be trained for months, weeks, or even months, like I said. So you need to track your experiments, right? How the loss converges, how is your gradient coming up. So all of these needs to be noted. For that, you can use tracking tools like MLflow, weights and biases, or the most common one, which is tensor board. Also, you need to decide whether you're going for cloud or on-premises infrastructure based on your flexibility, cost, and control. Okay. So if you want more flexibility, less cost, less control, you will go for cloud. If you want less flexibility, more control, cost is doesn't matter, then you'll go for a cloud on-premise infrastructure. That depends on your requirement. Right. Next, like I said, you'll do a lot of tracking, right? What are the things you'll track? You'll track the training loss, validation loss, perplexity. Perplexity is a parameter which will say how much your model is confused when it says a new word. For example, if I'm saying, let's say you understand Hindi or any languages to some extent, certain extent, right? But people are now speaking it with English a lot. So if I see some word new, for example, in French, okay, I have a limited knowledge in French, let's say. If I see a new word, I'll try to understand what could be the new word based on the words which was available to me. And if there is some English words in between, I'll get the context from there, right? So my confusion rate will be lesser, right? So that is perplexity. How much your model is perplexed seeing a new word. So lesser the value, better the performance. And then you will monitor your learning rates, lesser the better, and then gradients as well. How can you debug your model? First, you can check the gradients are correct. Okay, it's not exploded or something like that. Let's say, like, if it is hundreds and thousands, it means there is something going on wrong. So you need to normalize something like that. And also, you can visualize the attention weights. So mostly, like, it is more easier to visualize the attention weights with images. With text, it is a bit harder. Okay, in attention maps, you'll see, like, where your LLM is focusing, because to see, like, where your model is focusing, we are using C, like the word as C, which means you are having some vision to it. So visualization of attention weights with images are more easier than text, but still you can do it for text as well. And then there are possibilities for training instabilities. So how you can handle that is, first you can use gradient accumulation steps. So gradient accumulation steps will ensure that your training time is getting lesser. So basically the idea is that instead of doing backpropagation at every step, you will do it, let's say, after 4 steps. Okay, something like that is what gradient accumulation steps. Until then, the gradient will be accumulated. Just accumulation is nothing but just getting added together. Okay, and then you have mixed precision training. So, like, again, this is to make it more efficient. And then make sure that your initialization of model parameters is very carefully you have initialized it, because if you don't initialize it very well, you will get a lot of issues later, and your loss will be something like nan. Okay, loss will be a nan or zero. Like, if the gradient becomes nan, your loss will be zero. So your model will not get trained. Another important aspect while you do pre-training is making sure that there is a checkpointing and resuming training capability in the pipeline, because regardless of how much you handle the training pipeline correctly, there is a high possibility that you will get some issues and the pre-training will be stopped, right? So you should be able to resume your training from that stage. For example, you trained it for 2 weeks, okay, and then there is a sudden issue, and then your model got stopped. Maybe it is because of data, maybe it is because of RAM overload, maybe it is because someone restart your server, anything, right? So you should be able to restart it. So for that, you need to first ensure that there is a regular model checkpointing done, where you need to save your model weights along with the optimizer states, because without optimizer states, you can't resume your training. Okay, so the frequency consideration should be there, because reading and writing is always something you need to consider. If you are writing, let's say, in every 100 steps, it is going to take some time for it, right? So make sure that there is an optimal number where you are trying to save. Mostly, I feel like, one, or like, let's say, 2 to 3% of steps is an optimal number, is what I feel. Let's say you are training it for 10,000 steps, right? 1% would be 100, if I'm not wrong. Yeah, so 200 steps once is something a very good number while it comes to pre-training. Okay, and then make sure that you you save the checkpoints in an efficient format. For example, shadow checkpoints is something very good, because it will be able to load efficiently across GPUs, and pre-training is something we do it in multi GPU, right? So That is something you need to consider, and also make sure that you have compression techniques to store across based on your storage requirement. And then, like I said, receiving training should be something you need to enable in your pipeline. If you're using trainers like Hugging Face or PyTorch Lightning, those are something which have that capability by default. But if you're doing something by yourself, then you need to make sure that that is handled correctly. So for that, you need to handle your learning rate schedulers, data iterators, and also making sure that the reproducibility of results is there, like setting up the seed values correctly. Now we are now we are done with LLM training. But like I said, LLM pre-training is a very big process. All right. What if your model is not performing accordingly? Like, you're expecting a result, but down the line, you're seeing after, let's say, 5 weeks or 6 weeks of training, you're seeing that your model is not working. Your 6 weeks are wasted, right? So that is why people evaluate the LLM at runtime. So there is a checkpoint saved. They'll try to run on an evaluation pipeline. How we need to do that, we'll see now. So before we go into LLM evaluation, I would just like to ask you all to just subscribe to the channel if you haven't subscribed, and hit the bell icon to get the notifications, to get uh, workshops kind of video like these. Because here you can see we have almost, if you think like, we have almost come to the end of the video, right? Yeah, like evaluation is come. But no, you haven't. Just see here. Out of 62 slides, just 36 is completed, which means you are around halfway there, right? That is why I said this video is all you need for you to pre-train your own LLM, right? So what are the methods in which you can pre-train your LLM? Sorry, evaluate your LLM, which is pre-trained. Yeah, that is the correct one. There are five main methods. One, it is to use human evaluation. The second one is to use LLM assisted evaluation. Third one is to use match-based evaluation. The fourth one is to use benchmarks, and then fifth one is to use common metrics. Okay. Thanks to Artrain AI for uploading such a good image to make my life easier, explaining you all about evaluation. Because if you see, if it is green, it means it is very easy. If it is yellow, it is like not easy, not tough. And if it is red, it is bad. Okay. When it comes to cost, if you see, the most efficient method is to use metrics. In every way, it is to use metrics except versatility, because your most the metrics you have, right? For example, if it is accuracy or your recall, you can rely on it, but it is not versatile enough, right? So that is metrics for you all. When it comes to humans, the cost is going to be very high. Imagine hiring a human to evaluate the LLM outputs for, let's say, 6 months. You'll be paying him monthly salary, right? So human evaluation is always costly. But if you see, that is the most versatile method, right? It is the most versatile method and the most reliable, in my opinion. Okay. After you have something like metrics and all, because metrics are something which you have defined, so you'll rely on that. Or as much as you rely on metrics, you can also rely on human. But human is given yellow here because human has their bias, right? For example, if I'm asking you who's your favorite cricketer, or something like, if your favorite cricketer, let's say X, is a worst cricketer, is what the LLM says. What you will do? No, how can he say that? It's wrong, right? So that's where humans become less reliable to some extent, because the bias is there, right? When you go to LLM assisted evaluation, the cost becomes lesser than human. The scalability becomes less issue than humans. Still, it is very versatile as much as human, but the bias will be a bit higher, right? Because here there is the bias of one person, but the LLMs which are already there and trained, it has the bias of n people. For example, if n people worships one person as a good person, if the reality is that he's a bad person, that LLM won't accept, even if our LLM says like, it is a bad person, right? So that is the issue with LLM assisted evaluation. Next, we have match based. um as much as metrics is there, match based is also a very good method. It is like exact match. That's all. Okay, using regex or exact matches is what match based methods are, and then benchmarks. It's like uh, how can I put it? Um, if you have no way, right, to incorporate any of these methods, then you'll go for benchmarks. Benchmark should be your least starting point, so to speak, because it is average in everything. It will be average in cost, it will be average in scalability, it will be average in versatility, average in reliability, right? Because all are done by someone. Now, what is the importance of LLM evaluation? It is to assess the model performance and capabilities, because if you don't do that, what is the point of training? If I'm going to say I just trained it correctly without any backing for it, assessing the model performance, and it fails in real time, what is the point of training, right? And while you evaluate efficiently only, you will know the strengths and weaknesses. How is that? Because when you're evaluating, and if you find that your model is failing at one place and it is working at one place, it means failing is weakness and working is strength, right? So identifying that is an issue. And then you have uh, guiding further improvements and iteration. Because even if you see in Llama 3.2 paper, they would have emphasized on iterative training, right? So iterative training works on the fact that you will identify the strengths and weaknesses, and based on those weaknesses, you will suggest improvements, and that improvements will be used for further stages of training. And then you should ensure that there is a responsible AI development. For example, NSFW content should not be generated, something like that, right? So ensuring these also comes under LLM evaluation, because you're um, obligated to follow some ethics, right? So that is why. Next, what is perplexity and what are the other last metrics which you can use? Like I said, while monitoring, you can use perplexity, and perplexity is defined as technically exponential of the cross entropy loss. Okay, so the interpretation is that lower the perplexity, better the model performance is. Here, the limitations is that it is not always correlated to the downstream task, right? Because it is just going to see how much it is confused, how much it follows the task. It doesn't matter for it. So that becomes a limitation for it. So that is why perplexity is used as just to say another advanced version of loss function. Okay. And then you'll also monitor your training and validation loss that is there. What are the benchmark datasets and leaderboards you can use? First, you can use glue and super glue. That is something very common. It is to show see how much your model understands natural language. It includes tasks like sentiment analysis, textual entailment, and question answering, and so on and so forth. There is another variant of this dataset itself, which is super glue, and that is a more challenging form of glue. Let's put it that way, because it will emphasize more on the complex reasoning tasks. Okay, so here you know the understanding. Next, how much it has reading comprehension, how much it can understand the context and then answer based on it. For that, you can do a question answering kind of an evaluation based on context, and for that you have squad, Stanford question answering dataset. Next, there is Lambada, which is language modeling benchmark. I don't know why they kept it as Lambada. Still now, I don't know. I call it as Lambda actually. So what is this Lambada benchmark used for? It is used to test the model's capability to understand long range dependencies. Because if you see, one of the aspects of or the goals of LLM pre-training is to make sure that the LLM understands and holds context for a long length, right? So that can be ensured with the help of Lambada. Next, you want to make your model multilingual, right? So multilingual benchmarks are there. Extreme, Xglue, these are benchmarks which are used for cross-lingual understanding. And then you have uh, emerging benchmarks, new benchmarks like Big Bench, which will see how much your model has a wide range of knowledge, because Big Bench has different tasks, and that is on different domains. Okay, so Big Bench you can just see it as domain related benchmark, because if you see multilingual related benchmark is Extreme Glue, Xglue, and then for long context you have Lambada. For natural language understanding you have a Glue. For reading comprehension you have Squad. And then for domain understanding, you have Big Bench, and adapting to wide variety of downstream tasks can be done with the help of HEL, which is known as a holistic evaluation framework for language models, right? It has around 40 tasks apparently. Now, if you see what and all goals we had for pre-training, right? All metrics are evaluated. And now, when you have a task specific evaluation and a downstream level, right? When we have question answering, you can use metrics like exact match or F1 score. Exact match is nothing but accuracy score. Okay. And for datasets, you have square, natural questions, trivia QA, hotpot QA, and so on and so forth. And here you will evaluate both answers correctness and relevance. For text summarization, you have ROG, which is abbreviated as Recall Oriented Understudy for Gisting Evaluation. So this is basically actually created for summarization itself. This metric was created for that, and this can be used for you to assess how much the data is compressed and what content is selected is to to make it compressed, and the fluency in which the compressed content is expressed. So for that you can use ROG, and for datasets of evaluation you can use CNN, Daily Mail, XM, MLSum if you are using multilingual tasks, right? Next, if it is translation, you can use Blue, Meteor, and then for datasets, you can use WMT for named entity recognition, precision recall, F1 score. These can be used, which is to identify the model's ability to identify and classify named entities. For this, you can use Cornell dataset. Now, coming on to human evaluation. Here, if you see, actually, we are going through each of those methods, right? We already see benchmarks, we already see some metrics. Now we are seeing human evaluation. So, why is human evaluation or human judgment important? Because humans can capture something which automated metrics might miss. For example, I might have said a word which represents the same answer, but the exact answer would have been different, right? So, the automated metric will say, no, I'm wrong, but technically I'm right, correct? So, that is why human judgment is important. And also, assessing overall quality and coherence of model output is done better with the help of human rather than an LLM or any other methods for that matter. Anything which even comes closer to assessing the overall quality or coherence is LLM evaluation. That is why these two are very versatile. All right. As far as evaluation protocols are concerned, you need to first have a clear evaluation criteria, making sure that there is very less room for bias or margin of error because human tends to make mistakes. Same goes for LLMs. So make sure that your evaluation criteria is clear. And also, you need to make sure that your evaluators are trained for consistency. They should provide a consistent result, right? For one thing, they're saying one kind of a result, and then for a similar thing, you should have said a similar result, but they're saying out another result. So that consistency miss should not be there. So make sure that your evaluators know what kind of evaluation should be done. That consistency is very important. Now, types of human evaluation. What can you do? First, direct assessment. So whatever model, for example, our LLM provides output, we'll evaluate those. That is one. And then comparative evaluation. So we'll have different models ranking the outputs of our LLM. For example, let's say ChatGPT, Claude AI, and then Claude AI means Sonnet, and then Gemini. All of these will evaluate our LLM, and we'll evaluate those evaluation. Okay, based on like that, we will be just ranking it, and then error analysis, where and all our model failed. We'll just analyze and categorize those mistakes so that we can retrain accordingly. Here, the challenges are the subjectivity because humans are subjective, not objective. They have their own biases and then their own principles, philosophies, so to speak, and that will always have a impact on their judgment. And then it is highly costly, and then highly time intensive, and also scaling human evaluation to large data sets is very hard. The ethical considerations you have is evaluating your model outputs for gender, racial, and other biases because these kind of bias will be there in common website data. So you need to ensure that your model is not biased on these ways. And then you have data sets for these, to check if your model is biased. For that, you can check it against Vino bias kind of data set and all. And then you need to see how much it is fair across different demographic groups. So you can't just say like, I'll be just doing English. Even if you go for multilingual, yes, there will be a low resource language, but still you should be demographically balanced to some extent. Then comes privacy and security implications. So you should not leak any training data to the user, and also you should be vulnerable. Your vulnerability should be very very less to prompt injunctions. Like for example, jailbreaking is a method where it will break the characteristics of the LLM, and it will be allowing the LLM to speak in the way it was not allowed to speak. So it was not uh, protective and was enough. It was vulnerable to that prompt. So you need to assess those vulnerabilities, and then also it should be truthful and factually accurate so that you can reduce hallucination. For that, you can use benchmarks like Truthful QA, which will allow you to assess the model tendency to generate false or misleading information. Now, why you need to do evaluation? It is to iteratively improve your LLM. So for that, first you need to analyze the evaluation results where you'll try to identify the patterns in the model errors and weaknesses, and you will prioritize those areas which require improvement based on your goals. Okay. And based on that, you'll say like, these are the categories I need to improve. And you'll say that to the training people, and then they'll train accordingly. And then there is also data centric improvement. So what you will do is wherever you find that there is a weakness, you'll augment those training data in those situations, and then you'll train it for more number of times there. For example, in multilingual, let's say one language is not doing well, you will increase the distribution of that language so that the model gives more importance to that language. And then also, if you identify some bias, you will filter those data so that those bias are not there after that. When you come to model centric improvements, you will fine tune it for specific domains or tasks whenever you see in the future. And then also, you will experiment with architectural modifications. So, like I said, whenever there is a new architecture advancement comes, you can try to plug and play with your LLM. Also, hyperparameter optimization. So, it is about finding the optimal number of layers, optimal embedding dimension, and so on and so forth. That comes under hyperparameter optimization. And you need to find a balance between your computational efficiency and your performance. Continuous evaluation, like I said, if you do all of these as a pipeline, it will be an automated evaluation pipeline, and then you will get the model performance, and then you will improve it over time. Okay. So that is what is your evaluation side. Now, the aim of any LLM, it is to fine tune to a downstream task, right? You need to adapt it to a scenario, even to check how much it has adaptability, right? What people do is they'll just fine tune the LLM for a downstream task. Okay. So here in our case, like I said, we'll follow this guide and then we'll try to pre-train our own LLM. Okay. So what we'll do is we'll use the same LLM to fine tune LLM for a classification task. So fine tuning is a stage where you will adapt a pre-trained LLM for a specific task. So what is the advantage of using fine tuning over a model which is trained from scratch already is that you'll have a good language understanding already. Task specific data will be less required because it already knows the language and syntax and semantics which is involved in the language. And since these are there, there will be a faster convergence, and then there is a potential for better performance. Okay. So here our goal of fine tuning is to determine the sentiment, and this can be used in customer feedback analysis, social media, etc. So what we can do is maybe try to make a real time emotion analysis kind of a model. Okay. So for this, what we can do is we can prepare a sentiment data set where what we need to do is we need to collect a label sentiment data set, and then we need to process those, and we need to make sure that there is imbalance being handled, create train test splits, and then we'll fine tune it. So for fine tuning, what we need to do is usually we need to add a classification head, because initially it will be projecting it to the n tokens which are possible next. So if we are using it as just a classifier, right? Next token. I mean, like what classifier it is. We need to add a classification head. That is usual, okay? But we won't do that. We'll make that classification itself a generative one. And there is another option which is to freeze some layers. So either you can freeze or unfreeze the layers. That is completely upon choice. And also choosing appropriate learning rates. Like I said, those are hyperparameter optimization. So if you are having pre-trained layers, you can keep a lower learning rate because it is already trained. It will take some time to adapt. But if you are having some new layers attached, have a higher learning rate for those. And then selecting your batch size and number of epochs, that is also there. Keep your number of epochs very less. Okay. And when you are training the sentiment classifier, your loss function should be a cross entropy loss. Like I said, we are making it generative, so we'll use cross entropy loss. But what if you want to just say, like, the class alone? So if it is just binary, you can use BC loss, binary cross entropy loss. And if there is a lot of class imbalance, you can try to use focal loss to handle that class imbalance. I mean, as far as the loss function is concerned, but for handling class imbalance, like I said, one is focal loss, another one is to adjust the class weights itself. So there is a method where you can provide weights for lesser number of values being in the class. For that, there is a method. You can do that as well. So here also we'll monitor the training process. So here we'll not monitor the perplexity kind of metrics and all. Here we'll monitor the training loss, validation loss, and then we'll see the classification accuracy and relevant metrics like F1 score, precision, recall, and so on and so forth. Here we have early stopping models, early stopping at all, where since we are pre-training the model to avoid overfitting, we'll have early stopping at all. So some of the advanced fine-tuning strategies are, like I said, like we'll train the whole LLM, okay? But if you're freezing, right, you can gradually unfreeze few of the layers in future. So that is something which you can do. And then also you can do mixed expression training. Knowledge distillation is something a very good method. We'll see that later. Okay, we have a separate day for that. Um, so these are some of the methods. I'm not going to focus on a lot on fine tuning because fine tuning we have a separate section for that as well. But we are considering that also in the pre-training because that is how you'll be able to verify that your model has the capability to adapt to a downstream task. Okay, that is the aim of this fine tuning. So the metrics we have are accuracy, precision, confusion metrics, and you can do cross validation as well if you want to do that. Now, let's say we are ready with the model. What are the considerations I have for deployment of this model? First, I need to see if the model size is good. Okay, if it is not good enough, I need to prune to reduce less important weights. I can quantize to reduce the precision of the weights. These all will reduce the size of the model. Or what I can do is I can already create a smaller model and then train by distillation method so that it becomes deployable. In real time, inference plays a lot of important role. So optimizing it for latency is very important. So like latency should be very less and throughput should be very high. Making that to be ensured is very important, and also making sure that hardware acceleration is leveraged. For that, you need to use library like TensorRT, Onyx Runtime. There is Llama CPP, and so on and so forth. Right now, when you are deploying right in real time, there might be existing systems. So you need to make sure that your API which you are developing, like for your model serving, that should be compatible with those systems. And also, you should employ logging and monitoring to see your model working at the real time, and also monitor like whenever it fails you can update it continuously, so you can implement strategies for that as well. Now coming on to the challenges and what can be done in the future. The challenges in the LLM development are that you have a computational resource and energy consumption as an issue. Like I said, it is a large scale training, so computational resource is an issue. Bias in the training data is be there, it will be there. How you can handle that is another important issue. Usually LLMs are black box, so making it very explainable and interpretable, understanding how the model decides that this is my next token, that is a challenge. And hallucination is another challenge. So what are the trends and future direction in which the world is moving right now? One is continuous learning, right? So we have LoRa, where it will try to address the challenge of catastrophic forgetting, so that you can continuously make your model learn for the future, and then more adaptable to few shot and zero shot. So that, like with less samples, you can adapt it for new tasks, and then making the model more ethically responsible. Finally, the conclusion. As far as the recap is concerned, we have seen from data collection to fine tuning a sentiment classifier, everything is covered. And the key takeaway, if you would have seen, we have given more importance to high quality and diverse data, making sure that you have a careful pre-processing and tokenization, because those serve as your foundation data for your model. And then we see the complexity of the architecture being balanced with your computation environment, and then you are creating a training procedure which is, um, let's say, scalable in nature. And then we have seen the significance of evaluation and improvement over time, like an iterative improvement. That if significance is there. So what are the future of LLM? It is going to have a potential impact on every industry which is there, and there are lots of ongoing research and challenges and opportunities are there. We can see what we can grab out of those. But now, if you see, you have literally overloaded information of the whole pre-training pipeline of, anything and everything which is related to pre-training. In the 62 slides, you have all the information which is related to training process. So I hope you all would have liked this video. If you like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in the next video. Until then, happy learning.
Hello everyone, the wait is over. Welcome to the day 8 of the LLM pre-training course, where today is the day we are going to build GPT-2 from scratch. Yes, we are going to pre-train GPT-2 from scratch, and I'm going to follow the pipeline which I have explained in day 7, but with a twist. Rather than starting with the dataset, here I'm going to start with the model, and then I'll move on to the dataset and then creating the training pipeline. So this will be a two-part day, right? Day 8 will be about model building, and day 9 will be about creating of the dataset, and then creating the whole training pipeline, and then training it. So this will be a two-part day. Um, let's start with building the model. All right. So let me put an image of GPT at the right for a reference. So right now we have a reference of what is the architecture we need to start with, right? Let's start with the most complex component out of all of these components, which is nothing but our masked multi-head attention. So let me zoom that and keep that. So this is the component which we need to start with first, right? So let me first take some imports, import torch, and then for neural network, we have some other imports like from torch.nn, import, no, from import torch.nn as nn, import torch.nn dot functional as f. Okay, so these are some three important imports. Let's put it that way. Okay, let me rename the file as well. GPT-2 model. Okay, so here in this GPT-2 model, we'll have GPT-2 model. Let's call it a web model, and you will understand why. And for those people who find why I keep it as web model, you will have a surprise later. Okay, but yeah, let's keep it web model for now, the name. And here we'll do a def dunder init, super init is required, these are not required. So let's put a pass here. Okay, this is the architecture which we need to fill, and what are the classes we want. Okay, this is the overall model class. We'll fill all of those. Okay, the components goes this way. Okay, we need layer normal class. So that will be probably one of the last classes. The first one would be a masked multi-head attention class, or rather a multi-head attention class, because the mask is just a parameter which is provided. Multi-head attention class. So here also we'll just create multi-head attention dot module def dunder init. Maybe we can, this is not needed, this also is not needed. So here also we'll just keep def forward, and then we'll have it as pass. Okay, so we need to import that. Here it should have been like this, def forward self pass. Okay, so what all do we have here? And then we have feed forward. Let's create something for that. Feed forward class. So basically right now we are just creating a bone, like, a structure, what we need to do. This will help us to think better. And that module def dunder init. Here I need to remove these. This is not required. Is this here? Yeah, looking good. It's looking good now. Def forward self, and then another pass. Right. So layer norm is still there. Right. So let's copy this. I should have done that from before. People who have thought by now that, like, why Vasant hasn't just copy pasted things, please let me know in the comments, because you are better than me in this specific scenario. Okay, and if you are wondering about embeddings, right, you need not wonder, actually, because the embedding which is used in GPT are just you know dot embeddings, basically absolute embeddings. All right, so it will be easier for us to do that in the transformer model itself. So in the GPT-2 web model itself we'll do that, and if we feel, we can also add another component like embedding. That is also something which we can do. All right, so maybe we can have that embeddings class. Okay, class input embedding, and then dot module. Here it will be, I'm repeating the same issue. Copy, paste, embeddings, input embedding. Okay, so these are the things which we need to complete in this video. Okay, if we complete this architecture, we are completed with building an LLM by ourselves. Let's see one by one. Okay, so let's start with the embedding itself. All right, so where is the embedding class? Here it is. What all do we need? First, we need something called token embedding. Is the indentation is not that good, actually, for some reason. Self dot token embedding is equal to nn dot embedding In another embedding, what all do we need is, oh, I left something very important. GPT config class. What is the model name? GPT-2 web, and I'll add it as config. Here, first we need to actually provide our configurations. Let's see what are the configurations which are required right now. So let's start with something like a self dot oh yeah, think with dunder inits itself it's possible. Maybe we can, it is better we have it as a separate file. So I'll create something called a gpt2 config.py where we can have all the constants ready. Okay, what are the things we have? Vocab size, that is important. So that is 50,257. All of these are standard. Okay, context length, what we need, what we are going to train. For now let's keep it to 6. If possible we'll extend it. Okay, embed dimension, or we'll call it as d model. Usually d model is, let's have it as 512. Number of attention heads, let's have it as 8. Number of layers, maybe both 6. Okay, let's keep 6 for both. Dropout, will be 0.1. Dropout probability. Okay, these are some of the configs we require, because for example, just see now here, I'll import those from gpt2 config, import star. I need to import all of those values, and here I'm going to use that. For embedding, if you see, we require the number of embeddings, which is your vocab size. Okay, for how many number of tokens you need embedding, that is your vocab size basically. So here I'm going to initialize that. Self dot vocab size is equal to vocab size, and then we can call that here. Okay, and then the next one is d model. Okay, which is the embedding dimension. Self dot, so right now we are getting our d model. D model is d model, and then we'll also provide that because our embedding dimension is important, right? I hope the size looks good now. No, with this on the side, I'm not sure if it was clear before. So yeah, this looks good, better. Now let's have the position embedding. Positional embedding will be an, like, n dot embedding again, but here just guess now, like, what are the things you will be providing. If you guessed self dot um what was the name I kept, context length. If you kept it as self dot context length, then yes, you are right, because we are encoding the position, right? So self dot context length will be equal to context length, and then we'll provide that here. Along with that, self dot d model, that is no magic here, right? So it is going to be pretty simple for us right now. Okay, so in everywhere we need torch dot device. So device is equal to CUDA if torch dot CUDA dot is underscore available, else CPU. Okay, so device is very important everywhere. Actually this definition should not be here, it should be rather here. Import torch, then we'll have it here, device, right? Now in everywhere, then that will be imported. Self dot device equal to device. That ensures that you don't run into any issues. So let's see what we need to do for that now in the forward section. Okay, so here it will be input IDs. Okay, let's have it as X. Okay, so it is going to be batch size and then sequence length. Why? Because it will be for example, one sentence with 10 tokens. That's all. The embedding is not still computed, so we are going to compute that. So only it will have two dimension, so we'll have as extra shape. Now we need to create token embeddings. Token embeddings, let's have it as X token embedding. Okay, X token embedding is equal to self dot token embedding of X. Okay, and then here what we can do is we need to initialize another thing, which is self dot positions, which will be um, I think it is better if we do it in runtime itself. Yeah, so what we can do is positions will be equal to torch dot arrange of. Arrange is a function which will create numbers from start till end. Okay, so right now it is from 0 to max length, right? So we need to provide that. So it is going to be self dot context length. No, not context length, self dot sequence length. um, yeah, sequence length is what we need to provide here. And then you need to provide device here, which will be self dot device. Now you have the positions, you need to embed this. Okay, let's have it as position embeddings. X position embedding will be equal to self dot position embedding of positions. Okay, so now we need to add both of these. Okay, so X input embedding will be equal to X token embedding added to X position embedding. Okay, and here you need to note something, which is we haven't added a dropout yet. Usually we need to add a dropout because that regularizes things a bit. So we'll initialize that as well. Okay, but if we have the same name for everywhere, we'll just get confused. So we'll have it as self dot dropout for embeddings. Okay, and here it is going to be nn dot dropout, and already we have the dropout probability, so it is going to be self dot p equal to dropout p, and then we need to provide that here, self dot p. That's all. Okay, so now the input embeddings needs to be normalized. So X input embed, let's put return here itself, return self dot dropout embedding of X input embedding. Okay, now we are done with creation of input embeddings. Next, let's go on with multi-head attention. Okay, I said we will start with that, but input embeddings demanded it, so we just did it. Let's do with multi-head attention now. with multi-head attention, what are the things we require? Let's see that. Okay, so here, if you remember from our transformers construction itself, so it will take some things like d model, which is our embedding dimension. It will be of int type, num h, so number of attention hits it wants, so it will be also int. What is the context length you want? So that will be again an int value. Dropout, so actually what you can do is you can hard code these from here as well. Okay, that is also something which is a very good practice. But usually we keep input embeddings outside. All of these will be encoded inside, that's why I kept it. But we can also do this as well, later, like for example keeping this here, that will look neater actually. Okay, vocab size, d model, context length, device, and then dropout p. Okay, so if I do this, it will be even better to look actually, because anyway you're gonna initialize these parameters from the GPT-2 model, so it will look better. Let's keep it that way. Okay, so vocab size will be an int value, d model will be an int value, context length will be an int value, device will be torch dot device, and then dropout p will be a float value. Okay, now let's start with multi-head attention again. Again, we are just jumping. Sorry for that. First thing we need to see is here, write an assertion statement to make sure that d model is divisible by the number of hits. So for example, if I go Python, what was the consideration we had? Let's see if that works actually first. 512% 6. So the remainder is 2, which means it won't work. Let's try for 8. It is 0, which means it will work. As simple as that. Okay, because you're going to split your embeddings across the heads, right? So it is very important that your embedding dimension is divisible by the number of heads. So let's keep both of these same. Number of layers also 8. If you keep 6 as well, it will work for number of layers, but number of attention heads needs to be 8. Okay, so yeah, right now this should work for us. Here with assert, you need to provide a statement as well, where if this statement fails, what it will say is d model is indivisible, or something like d model should be divisible by num h, something like this, so that if you click some other config, you will just get a warning stating that this is an issue for you. Okay, without even executing the whole and then wasting some time. So let's add all of those values in here. So it is going to be self dot d model will be equal to d model, and then self dot embed dimension will be equal to self dot embed dimension, not embed dimension, num h, sorry. So it is going to be num h equal to num h self dot context length equal to context length, and then self dot p, let's have it as dropout, attention dropout is equal to dropout. Okay, so these are the things which is required. Right now, self dot qkv. Why we are initializing like that? Because in the official implementation as well, all of these would have been created together as a single one. So we'll also try to do that, right? So it is going to be nn dot linear, where it will be d model comma d model cross 3. Okay, basically we are saying that it will be 3, so that will be splitting at that dimension. Okay, and here we need to provide a bias as well, stating that it is false. Okay, we don't need any attention bias. And then we need a projection. Actually what in GPT official name would be something like CATTN. This is how it will look like actually. Maybe we'll do it in one future time where we'll convert this architecture in such a way that this is compatible to Hugging Face. We'll do it in some time. Okay, so let me know if you want that in the comment section. I'll try to do that. Self dot projection will be equal to nn dot linear of d model to d model. Okay, basically this is to uh, comprise all of this information together. Okay, um, next we have self dot attention dropout equal to attention dropout. um oh, we already initialized that, right? I think it should be simple. Yeah, this is good. Now let's implement the forward function. Here we'll get x. Okay, that is usual. What are the things we required here? Batch size, sequence length, and embedding dimension, or we usually call it as d model, right? So d model, both of all of these three are there. So why? Because you have embedded it already, right? So embedding dimension will be added, and then it will be provided to the masked multi-head self attention. Basically that is what we are creating here. So it will have 3 dimensions rather than a 2 dimension, how it was for embedding. Okay, now first we need to make this with weight layers. Okay, we need to add some weights to this. So we need to call self.qkv of x. So basically right now it would be something like this: batch size, sequence length, d model will be converted to batch size, sequence length, 3 cross d model. Okay, so these will be the things there. Now we'll make this in such a way that this is available for multiple heads. Okay, so for that we'll call qkv equal to qkv dot view is basically like a reshape function. Basically what is the dimension we require is from this. Okay, I need to take out this needs to be converted like batch size, and then it should be num tokens for query key value, so 3, and then number of hits, and then head dimension. Okay, so we haven't computed the head dimension. Let's compute that. Okay, so it should have been here. Self dot head dimension will be equal to self dot d model flow divided by self dot num heads. Okay, so that was also something which is required. Now here if you see, we need to do this, right? How are we going to do this? We need to view it in such a way that it should be batch size first. We already have that. So next we need the num tokens, right? Number of tokens is nothing but your sequence length. So it is going to be sequence length, and then it should be 3 hard coded, and then self dot num heads, and then self dot head dimension. Why is this even possible? First, if you see, it would have been 3 cross D model, which will be something like a 3 comma, which you can make it actually. If you do it step by step, right? You can also make this where you will get this input, okay? And then you will convert it as 3 comma D model, but we are doing it in a single step, okay? That is what is happening here. So right now it is 3 comma number of hits comma head dimension. So you have the values for QKV together, but we need to have it as 3 as the first, because you then only you'll be able to separate as QKV. Okay, so for that what you need to do is, so basically how I require here is, I'll show you. From here it should become something like this. Okay, I'll change it from here. 3 comma batch size comma sequence length comma number of tokens comma head dimension. Okay, basically this 3 should come first, right? So that is what is required. So for that what you need to do is use a function known as QKV dot permute. There is a function known as permute in torch, where what you can do is you can just change the dimension. Okay, so for example 3 was at the second dimension, right? 0 1 2. So 2 will become first, I need 0 next, and then I need 1, right? So 1, and then what I have here, 2 is already done, so 3, right? So it will be 3 and then 4. Basically the array will be rearranged. Okay, so it will be 2 0. Just let me check first. Once it was like this, 2 0. Yeah, that is where I got confused. I was just thinking. So it should have been 20314. Okay, why? Because 2 is basically the number which is QKV, but you need to split it across head, right? So it would have been 2 batch size, and then the number of heads to which the tokens will be applied. Okay, so it would be like number of heads first, and then sequence length for that. Okay, so this is how it will be splitted now. Now what we'll do is we'll just have it as query key value from QKV. Okay, now how it will be looking like is, I'll just copy this. So it will be like 3 star all of these. Okay, for each of those there will be a batch size, num head, sequence length, head dimension kind of a structure. All right, so here we'll see if there is a dropout or not. Okay, so we have a dropout here. Okay, always there is going to be a dropout. I need to put as float here. So what we are going to do is instead of writing scale dot product attention by ourselves, which will be like a learning curve for us, but it is not very efficient. We have already seen how to write that, right? Like Torch has optimized it better in something known as NN dot functional. Okay, in functional itself, if you see f dot scale dot product attention, it will have a value, and if you see here, they would have implemented it. Okay, they would have implemented it, and that is what we are going to use. Okay, so you can see what are the things it requires. Query, we have it. Key, we have it. Value, we have it. Attention mask, we do not need to provide, because if we say is causal, it is going to work. And then dropout probability, it is going to be something which we are going to provide. Is causal is going to be false. Okay, these are not required, right? So it is going to be, um, let's put it as attention underscore x. Okay, x is computed with attention. Basically, this is a context vector which has some attention to it. So nn dot functional, already be imported it, right? So it will have it as f dot scale dot product attention of query equal to query, key equal to key, value equal to value, attention mask equal to none. We'll see what we need to do, like if we want to make an attention mask, because if you see, when you send is causal to true with the context length and all, right, it will try to generate the mask by itself, basically inside. Dropout p will be self dot dropout, attention dropout, and then is causal, we'll get that as well from the user. Basically, is causal is going to be true, right? For us, we are not building transformer, so let's have it as is causal to true. Okay, so now we have computed the attention, but if you see this attention, what shape it will have is, it will have something like a batch size, num head, sequence length, head dimension, similarly like how it was before, but we need to combine those together so that it is concatenated as from the multiple head to the single head. Okay, that concatenation step, how it will look like is, uh, concat attn x will be equal to attn x dot transpose of 1 comma 2. Why? These need to be transposed. Sequence length should be first, num head should be second, so that num heads and head dimension will be combined together. Okay, we need to make sure that those are contiguous. Okay, because we are combining it from different places, so those should be contiguous, and then we'll view it in such a way that batch size comes first, sequence length comes second, and then it will be d model. Okay, where do we have d model here? Yeah, so it will be d model. Okay, so basically we have combined it. Now we need to send it via projection. Attn projection x will be equal to self dot projection of concat attn x. Okay, right now I have my attention completed, so I just need to return this. So here I didn't mention it, right? So here it will be a two-step process. It will be batch size, num head, sequence length, head dimension 2. Batch size, sequence length, num head dimension, head dimension, which will be combined to batch size, sequence length, d model. Okay, this is how it works as far as the attention is concerned. All right. Here it is just a linear layer, so the shapes are not going to change. Okay, now let's see how to implement the feed forward. So right now we are in feed forward. Let's do layer num later, like that is a common thing, right? Let's have it later. So for feed forward, what are the things we require? Let's see that, right? So here you will need something like a D model, and then you need something like a DFF. Okay, so what is DFF? In D model, we say embedding dimension, right? There is a dimension specifically for feed forward itself, which people usually call it as intermediate dimension. Usually it is D model star 4 times. Okay, I'll have it as a relative, but that applies only if your model is very small. If you go for like a big model, it will have 4096. You need to have 16,000. That is not something very feasible. um, but like it is usually larger the better, because when it is a larger network, it can understand the information which the masked multi-head attention has captured better. Okay, so we need D model and DFF. Other than that, we don't need anything actually. um, so now how we can do this is, it will have two linear layers. Okay, self dot fully connected layer 1 will be nn dot linear of self dot, oh, I should have initialized that, I forgot it. Self dot d model equal to d model, self dot dff equal to dff. Okay, so that is feed forward dimension. Let's have it there. So it is going to be self dot d model cross self dot dff, and the second one will be the straight opposite. Okay, fc2 will be self.dff comma self.dmodel. You're up projecting it, you're down projecting it. It is better if you write it like this: up projection, down projection. That is where you'll have those, like understanding clearly that this is how it works. Okay, so we have self mod up projection and down projection. Along with that, we need dropout. I forgot that. So dropout would be there. So this is gonna be an int value, this is gonna be an int value, and this is gonna be a float value, right? So self dot dropout will be nn dot dropout of self dot dropout. This is like the thing which we did with like input embedding. Let's just put it as ff dropout, like how we are maintaining it, right? um okay, we haven't initialized that. Self dot dropout equal to dropout. Okay, so self dot feed forward dropout is also ready. Now we need to add another thing, which is self dot jelu. Jelu is the activation function which is used in the paper, so we'll also use that. nn dot jelu. How it works is, basically you have your input x. Okay, I haven't added the type there. Torch.tensor. Where is tensor? Here it is. I should have added those there as well. X is to torch dot tensor. Do I have anywhere else? Sorry for the disturbance caused. So I'm just adding typecasting everywhere, so that it will be actually easier. So if for example, there I was doing something like a x dot shape, right? So if I did now it will show automatically. That is a better way. Like, for example, it was QKV here. If I had something like a QKV is to torch.tensor, you'll see a difference now. See, QKV.view, QKV.permute. It is always better to have a typecasting because with VS Code, right, it will give you the functions directly. It will make your life easier. So I usually do that a lot. Um, so it is going to be tensor. So given an input, it is going to be very simple. We are not going to get batch size, sequence length, nothing. Okay. So self dot not approach x will be self dot up projection of x, and then we'll send it to Jelu, self dot Jelu of up projects, and then down proj x will be self dot down projection of up projection x, and now we'll drop out it. ff out will be equal to self dot ff drop out of down projection x, and then we'll return that, return ff out. Okay, so right now our attention is done, our feed forward is done. So basically it would have been at the dimension, so whatever it was, so let's say it was d model, right? So it would have been something like 512 converted to 2048, because that is what is our DFF, because it is basically the 4 times. Okay, and then another converted to 512. And the good part is you'll learn something out of this. That is why it is there. Now let's see how you can implement the layer norm class. Okay, add and layer norm is different. Okay, adding is something different, and layer norm is something different. Okay, right now we are just seeing how to do layer norm. Okay, add and layer norm will do it in the model itself directly. So for layer norm, the function which we are going to use is a simple like z-score function. Okay, so for that you will find the mean, the variance, and then you'll do a standard root for variance, so that you'll get the standard deviation. But here with that we'll add an epsilon, so it will, the formula would be something like this. Okay, this is what we will be implementing here: x minus mean by standard deviation. Okay, that's all. And then here we'll just add some other values after this. Okay, so let's say you get an output here, you will be doing scaling. So it is like alpha star x plus beta. Okay, so it will be alpha star, let's say it is norm x, it will be converted plus beta. Okay, this is the formula basically for layer norm. So for layer norm, you need one parameter, which is EPS, and that is float. Okay, and here EPS value will be like epsilon value, basically 1 e minus 5 or 1 e minus 6 is a very common value. Okay, you can also hard code it there as a keyword argument rather than a just normal argument, because if it is not provided it will take a default value, right? So here we need two things. One is epsilon being initialized, along with that self dot alpha, which will be nn dot parameter. So these parameters are learnable. Okay, that alpha and beta are learnable. So if you are wondering how the theory of all of these work, please make sure that you watch the transformers theory video, because I've explained each and every component in very much detail as much as possible. Okay, So how another parameter will be initialized with is it will be just torch dot ones of um, d model that needs to be provided here. I forgot that. Um, so it is going to be d model is to int comma epsilon. Why I put d model before is not because it is a very important value, because arguments come first and then keyword argument. Okay, if you put d model first and then epsilon first and then d model second with values for epsilon, you will get error. Okay, so we need to get d model. So it will just here what it will do is it will just create a 512 number of ones. So it will be the same for beta. Basically the normalizations will happen at the embedding dimension. Okay, so here what we need to do is first find the mean, right? So mean will be equal to x dot, oh, we need to provide x here. X is to torch dot tensor. If I see now x dot mean, simple, dimension will be -1 because at the last dimension, which is embedding dimension only, I need mean, so I keep the dimension to true. The variance will be equal to x dot var. So this x dot var function will compute the variance. Okay, again we'll be doing it at dimension -1, which is the embedding dimension, which is the last dimension basically, and then we'll set unbiased to false. Okay, and then keep dimension to true. Okay, so here we are going to normalize the x, right? So x normalized will be equal to, see the formula, x minus mean. If you remember the Bodmas rule, subtraction will happen later, but x minus mean should happen together. So we need to add a bracket there. X minus mean torch dot square root of, here it should be square root. Okay, because standard deviation will be square root of variance, but here just rather than square root of directly to variance, we'll add something like a epsilon value to it. Okay, so celebrate epsilon. Let's put it as learned x normalized. That would be a good way to put it, because we are adding two learnable parameter for that, right? Self dot alpha star x normalized plus self dot beta. This is where the normalization becomes a learned normalization. Okay, learned x normalized. Okay, so this is how the layer norm happens. So right now, if you see, our embeddings is done, layer norm is done, feed forward is done, multi-head attention is done. We are coming into the final and the most interesting part, which is to construct this architecture here based on all of the things we have created here. Okay, this is where it is going to be very interesting, right? So first, here I need to take out all the values which are there in config. Okay, here I'll just put it as a 2 tab. That is when it will become easy for me to initialize things. Okay, self dot vocab size will be vocab size. Self dot context length will be equal to context length. Self dot, what is it, d model, yeah, d model will be equal to d model. Self dot num heads will be equal to n heads. Self dot num layers equal to n layers, and then self dot dropout probability will be equal to dropout probability. Self dot feed forward dimension will be equal to feed forward dimension. And just it is boring, like it is always boring. Self dot um, mhm, APS is epsilon equal to epsilon dot device equal to device. Okay, every initialization is done finally. Okay, now coming on to initialization of those, which is self dot. Yeah, just now I forgot. If you remember, this will be a stack, right? And that is why I wanted to add that here. So it will be something like GPT block. We need to create that. Okay, it will be GPT block, which we need to create right now. Oral model classes later. Still, the fun part remains actually. GPT block class GPT block tenant dot module def dunder init of self super dot dunder init. So here we need to first integrate those. These are not required right now. We need to integrate those here. So here what we are going to do is we are going to just combine these blocks alone. Okay, that is what we are going to do. Here what are the things we required? Actually, here we don't require dropout in feed forward. Okay, let me put it as feed forward out here itself, because those dropouts will be done in here itself. Okay, we don't need dropout here. I'll just take this out. Yeah, looks good. So we need to first take out all these values, right? So what I'm going to do is I'm just going to copy these. Okay, paste it here, because I'm not going to provide the parameters again, right? So I'm just going to take all of these, have it here, and then initialize my architectures. Self dot multi head attention will be equal to multi head attention of self dot d model. What are the things? Self dot num heads, self dot context length, self dot dropout. Okay, so these are the things required. And then for feed forward, what are the things again which is required here? Feed forward, which will require self dot d model, self dot dropout. Oh no, dff I guess. Yeah, here vocab size will be required, I guess, because we are not initializing embeddings. Okay, and then we require two layer norms. Okay, so it is going to be self dot layer norm 1 will be layer norm which we created now, self dot d model self dot epsilon. We are initializing it as two stages because if you remember, those are learnable, right? So that is why. Here you can see layer norm 1, layer norm 2, mass multi attention, feed forward, all are done. Now this flow which you are seeing right now, we need to implement that in the forward. Okay, let's see that. Def forward self and x, which will be a torch tensor. Here first what we need to do is take the x value like before norm, something like that. Before norm x will be equal to x, um, self dot norm 1 of x, um, x norm x1 norm, probably x norm 1, we'll have it as x norm 1. Okay, and this x norm 1, let's have it as x itself, it will be easier to maintain the stage actually. um, X here, and then we'll send that x to self dot multi-head attention of x, and here if you see it will be batch size, sequence length, embedding dimension, the same shape will retain hereafter. That is not an issue. That is one of the main advantages actually. Here we need to initialize a dropout. Okay, so self dot dropout, let's put it as norm dropout, or what it is. I'm not sure. Let's have it as add the ln drop. Okay, add ln drop because it is used in add and layer norm section. Self dot drop out p. Okay, so I need to call that self dot add layer norm drop of x. Okay, so right now here we have, okay, we got x before norm, we have normalized it, we have sent to attention, we have got the output which is normalized. Now we need to add that with the before norm. Okay, we have a before norm here basically. Actually I guess the norm one shouldn't be done here. Let's see. um okay, maybe I think um before add would be something, because uh, this is a confusion where like every time I implement I'll get this confusion whether I need to add before or after. Let's see if this kind of an architecture works. If not, we'll go for having this before norm x later. Okay, before norm um, after attention. Okay, before norm after attention. Here I need to first add that, I left that, so x will be equal to x plus before norm I, before norm x. Okay, so that is how x will be here before norm after attention. I think even here before attention, this is good. I'll have it as before ffn, that is better. Okay, now it will be layer norm 2 of x, self dot feed forward of x, add layer norm drop of x, and x will be equal to um, before norm before ffn. Here it is. Okay, this is how it will be combined. Okay, and finally that softmax and all we'll do it in the main function. Okay, right now I'll just return the x here. Okay, we need to replicate this for num layers, that is why this is kept as a separate block. So self.gpt block will be equal to gpt block, and then other than this, what are the things you require? We will require a final layer norm, self dot final layer norm um, will be equal to nn dot layer norm. No, no, why nn dot layer norm? We have already initialized it, right? Layer norm of um, self dot d model. Okay, so here if you see the gpt block is a single block, right? But like I said, this will be for n layers, right? So we'll just replicate it. All right, So what we need to do is we'll just call something called nn.sequential of here. We need this. We'll have it for later. Okay. Actually, it is always fun to combine together rather than coding it from scratch. The fun part is always when you combine these things together because that is where you feel like you are really constructing the architecture. Um, so how much we want? So for underscore in range, so basically this star will replicate. Okay. So for range, the num layers, self dot num layers. Okay, for the number of layers we'll have the number of blocks. Okay, star will make sure that all of these are combined together in sequential, and sequential is like one will be sent to another. You need not manually send one layers to another. So thanks to thoughts for that. Self dot final projection, let's put it that way. Here you can see, right, there is a final projection. This place, right? Actually, it should not be embedding T. It should be named as projection. Okay. So the embedding T, it is named as like that because that is where you will convert your embedding to vocab. Okay. So how it will look like is something like this because here you are combining like making your tokens as embedding. It is the reverse here. You are making your embeddings as token. That is why it is named as embedding transpose, but it's not like just that. It is like nn.linear of self.d model across self.vocab size. Okay, and make sure that the bias is set false here. Okay, here I think I need to provide that here as well if I'm not wrong. Where was that feed forward? Let's see if there is a training issue, we'll understand. Usually if you keep bias, right, there will be an issue while training. So how the forward of the transformer will look like? First we'll compute the embeddings, right? So we need to take that as well. I didn't take that here, right? So it should be self dot input embedding will be equal to input embedding of self dot vocab size, self dot d model, self dot context length. It is just going on, but it has been fun building it from scratch. Just let me know how much you enjoyed today, because I enjoyed this very much implementing it from scratch. So how are we combining it? First, you'll get the input IDs, right? So let's put it as input IDs. Okay, it will be a torch tensor list actually. Torch dot tensor. Here, what we'll do is we'll compute input embeds. Let's put it that way because that is only gonna make sense. Input embedding of input IDs. Now we have computed the input embeddings. Now it is time to pass through the transformer blocks which we have created, which is the GPT blocks here. Okay, so the GPT blocks are going to be providing something like maybe GPT out. Let's just put it that way. GPT out is equal to self dot GPT blocks of input embeds. So that will give us a value. Okay, so here we are going to now say like see the embeddings are going to be projected to the tokens again. So usually we call it as logits. Okay, so I'm going to call it from now. There is going to be normalization, that is later. Okay, logits is equal to self dot, here actually we need to first do a normalization. GPT out is equal to self dot final layer norm of GPT out. Okay, and then here logits will be equal to self dot final projection of GPT out. Okay, so here we have the logits. We'll just return the logits. If you're wondering where the softmax happens, the softmax happens when you do decoding. That will be in the subsequent videos. Okay, in this video, which is day 8, we have just implemented GPT-2 model from scratch. Okay. In the next video, which is day 9, we'll create a torch dataset, a torch data loader. We'll collect some datasets from internet, mainly from Hugging Face, which are pre-training datasets, and then we'll just process it. We'll make sure that we write a pipeline which is good enough to handle large amount of dataset. And then what we'll do is we'll create a training pipeline, and then we'll create the model which is pre-trained for a specific use case at the later part. Okay, this is the way forward. And yeah, right now we are just moving on to advanced points. Okay, so yeah guys, I hope you all like this video. If you all like this video, please the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in another amazing video. If you like me calling amazing, um, please hit the like button. Okay, cheers. Hello everyone, welcome to the day 9 of the LLM Mastery course. Today we are going to see about collecting different data and processing it and then creating a torch dataset and a data loader for pre-training mini GPT-2. We already built mini GPT-2 yesterday, and today we are going to see how we can process the text in different formats so that it is possible for pre-training. Alright, so that is the aim here. The installations will be required are just datasets, and that's all. Just datasets enough. And for this, you would need some things. For example, you would be required to mount your drive. Make sure that you mount your drive because the data will be pretty huge. You can't do the whole thing in Google Colab itself. You'll be storing things in local. So for that, it is better to mount Google Colab so that we can store the datasets there. So for me, here you can see my dataset is now mounted. My drive is now mounted. I have taken the liberty of searching the dataset prior to the session because this will involve a lot of time, like to understand data and then process it. If I show everything in live, it will be delayed for you all. So that is why I've taken the liberty of exploring the dataset offline. So here you can see I'm using a dataset known as CC OpenWebTX. So if you're wondering what is OpenWebTX, OpenWebTX is the dataset which is used by GPT-2 for training. Like OpenAI used this dataset for training, but we are taking a subset of that. Okay, we are not taking the whole real dataset from there. Rather, we are taking the subset of a dataset which is available in Hugging Face. Okay, thanks to the person Keremp, whoever it is, because they are making our life easier. Because without them, it will be harder for us to make a sample like this because it is around TBs of data. Okay, so right now we are having 1 lakh samples here, which is text and target. So this was a good data set actually. It was saying if there is a text and there is a text which is positive or negative. Okay, that is what is this data set all about. But we don't need sentiment analysis here, right? We need data being generated, like story kind of a generation of one token after another token. So target is not required here. We are removing that column. We are seeing if the dataset is having the say only column. Yes, it is. And then we are running the function which is known as save to disk, which will basically what it will do is it will store the arrow files in your local for which they have used an implementation known as fspec. Basically it will be like cache. Okay, it will store like and then it will be loaded in an instant actually. So it is a very good format to store if you are having temp data. Okay, like temp means intermediate data. So this save to disk, after this I'll be changing it. It's not a rigid format. Okay, I'll be processing it further. So for that cases it is better to use save to disk. Okay, now there is another data set. So OpenWeb is an old data set, let's put it that way. It is 5 to 6 years old, but there is a very new data set in Hugging Face which is created only for pre-training, and you can see it is better in length and the format looks even more better than how it was there in OpenWeb, because this is a data set created by Hugging Face especially for pre-training, and this even outperforms the major pre-training datasets which are there in the hub. Okay, so let's see how we can use this. So the dataset name is FineWeb 100K EN medium. Okay, And if you see, it is not there from Hugging Face because this data set actually has TBs of data again. It is even more in size. For example, it has around 5 billion pairs, if I'm not wrong. Just pairs, I'm saying. 5 billion pairs means 5 billion sentences. And in 5 billion sentences, it will be trillions of tokens. We can't load that even in our local, right? So I thought, okay, let's take a sample. And luckily, there was this person who had a 100K sample. And then I'm just using that. Okay. So you can see now it is loading. And this is sample data. But here, if you see, we have only text, which means we are good enough to go for the next step. You guys need to run this, okay? CP-R pretrain, because we are saving things in pretrain, okay? Make sure that those are mounted in Drive, because with Google Colab, at any given point of time, you might go out of memory, out of session, things like that. It is a very irritating aspect. So what you can do for that is just put it in your drive whenever possible. So for example, right now data is downloaded, data downloaded stage is uploaded, something like that. Okay. I already have those in my drive. So what I'm going to do is I'm just going to start with data processing. And here, if you see in data parts, I'll have something like a process final JSON data, but those are not required. Okay. Here, what I'm going to do is data parts is to 2. Okay. If I give that, sorry, this is how you will get. Make sure that you comment these. Okay. When you execute, here I'm concatenating this data set so that both are concatenated, becoming a single data set. For that, there is one condition that you need to have same column. For example, here there is only one column, that is text, and it is a common column. All right. So make sure that you have a common column and everything is having the same structure, something like that. So now the data is combined, and here you can see it was 1 lakh and then 99,996. So it became 1,99,996. Looks like an offer number. It is always good enough to first convert it into pandas to do only one thing, which is to drop null values, because with open source dataset there is always a possibility for null values. And here, if you see, it is 1,99,996 rows, and if I put this now, it is 19 rows, which means there is around 87 rows. Yeah, 87 rows which has null value, and that is very harmful, right? So that is very important. Make sure that you remove duplicates. For us, there won't be any duplicates, but if you want, what you can do is just do pretrain data df equal to pretrain data df dot this will drop only exact duplicates. Okay, duplicates. But if you are seeing some closer kind of duplicates, it is upon you to write a logic so that duplicates are removed. So right now, our job is to make the life of the model easier so that it will learn faster and give us a better result. That is the aim here, right? So here, what we are going to do is we are going to just normalize the text so that it will understand that, okay, it need not generate any capital letter. So the learning curve will be a lot easier. And also, I'm just taking the first 2000 characters. Okay, that is what this normalized text does. Okay, here you can see my dataset is there. I'm mapping a function. So basically what it will do is it will go through each rows, and in each row it will apply this function. Okay, that is what happens with map function. Here in this function, what I'm going to do is I'm taking the text column, I'm lowering it, so everything will be in lowercase, and here I'm taking the 2000 character. Why? First, if you see, we consider our context length to be 256, right? At some point of time we may make it right, well, that is for the later stage, but we are considering it to be 256 right now. So the words approximately which would be there in this 256 token would be around 170 to 200, because there is a, let's say, unwritten rule that the tokens will be words into 1.5 times. For example, if it is 170 into 1.5, which will be 170 plus what it is, 85. So something like 255, something like that, closer to that. So it is 170 to 200 is what I'm expecting, and the average word length would be around 5. Okay, so 5, so it will be 200 into 5, which will be 1000 characters, but we are providing 2000 because if we think, okay, I'm gonna run it for 512 context length, this will be even supported. Why I'm doing this? Two things. One, it will be lesser in context length, and it doesn't make the model life easier. That, let me put that way, model life easier is making it lowercase, but when you make it shorter, your storage will become lesser, right? Because these will have let's say 15,000 characters. That kind of image samples also will be there, but we don't need that, right? We are supporting only 2 to 6 context length. Why do we need to store extra data? So we'll just remove those. Okay, and if you combine those, with the map function, you'll get a new data set. That is what I have written here. You can just override the same data set as well. That is your wish. If you run this function on this data set which we created from the pandas data frame where we dropped our nan values, which is missing values, we get this pre-trained data processed. Okay, here you can see it took me around 24 seconds for just 2 lakh rows. Imagine a billion of rows, it will just take days. As simple as that. Here I'm gonna add a column. Okay, it is always best practice to do that. Why? I'll say that later. Have, once you combine things, or even if you have a single data set, make sure that you add a id column. For me it is simple data set here, so I'm just using index kind of a function, but in real time you should use something like a uuid number generation. Okay, if you put in Chrome itself or any browser you have, or even ChatGPT stating that generate me a function to generate a uuid number, create a function to do that, and ChatGPT will give you that. It is very simple. In Python itself there is library for that. Why it is there? Because in real time, if you have that many number of data, right? For example, I said millions of rows, let's consider in that way, it won't be enough for you to store in your RAM. Okay, you can't load the whole data set. So what I usually do is I'll store each data set as a JSON file. Okay, so for that, what I use is, for the file name, I'll use ID. Okay, that is why I create ID column. But yeah, it is your wish. If you want, you can do that, or generate the ID at runtime. But it is better to have as a metadata in your data itself, so that at any point of time, if you want, you can just check your ID where it failed, something like that. Okay, that is why it is there. Now let's run these. So it is taking around 30 seconds here, you can see. And here we'll also add the ID column, like I said. And once that is done, I'm not going to save it. But here you can see, again, it is a milestone, right? It's like a checkpoint. You have processed your data set, you are added your ID, it's like closer to your final data set. So what I'm doing is I'm saving to the disk as process final, but I have it already, so I don't require that. But you make sure that you execute this as well. Okay, guys, don't worry, just data collection and data pre-processing alone happens in this walkthrough kind of a format. After this, again, we'll code everything in live only, so you need not worry about that. So here, pre-trained data processed, which we created here with columns added, ID, we are just shuffling it. Okay, we are making sure that the orders are different, because the way it is concatenated is the first data will be about let's just say the first data will be about open web text, and the second data set will be about fine web, because that is how those are there. Here we are shuffling it so that it is not in any order, it is in a random order. Okay, so just giving some difference to things. So now I'm just selecting the first 10,000 rows, because we are not doing real pre-training, we're just doing a mini GPT-2. Okay, so I'm just taking the first 10,000 rows here. That is what happens in select, and that is why we shuffled. Okay, to make sure that we take data from both. And here you can see I have a function to save rows as JSON. I'll go through each row, I'll take the row of ID, I'll convert it as string, and I'll add it as .json, and then I'll store it with combining to the saved path. Okay, so for that, here you can see there is a function which is pre-trained /final/JSON data. That is where I need to store. So if I run this, it will create a directory if it is not there, and it will save there. Okay. Make sure that you execute these two functions as well, so that your final JSON data is also stored in your drive, so that you can download it and continue the session in VS Code, how we are going to do right now. Let me see you with data loader and data set. Right now, our data pre-processing and data collection stage is completed. Next, we are moving on to touch data set and data loader.
Hello everyone. Since our dataset is now ready, which is collecting it and processing it, I've loaded it in my local. Here you can see there is min GPT-2 pre-trained data, which was the data we created there. In that, there will be a folder known as final JSON data in which all the JSON are available. So right now, I'm just going to create a file which is GPT-2 dataset.py. All right. So when I create this kind of a file, you might know by now that we are going to create a torch data set and a torch data loader. Okay. So these are very simple. You need not worry about anything here. Let's start with some imports, which are very important here. From torch dot utils dot data import. I hope it will be visible. Let me zoom it a bit for you all. Yeah, looks good. Um, from torch.utils.data import data set and then data loader. Okay, these two are needed. And then from transformers import GPT-2 tokenizer because we need that tokenizer. Okay. Um, let me check if there is my mistake in that. Auto tokenizer is there. Okay, let me use that. That is not an issue here. And here, if you see, we have everything as JSON files, right? So we need to use those JSON path. So for that, we need glob. Okay, we need to get all the file paths. So from glob, import glob, and then import JSON. Okay, these are the imports which are required. Right now, let's create the data set. First, let's start with creating GPT-2 data set. And that is going to be a torch data set. So we are going to override that, right? So first, we are going to create that def dunder init, and it is done the super init. Thank God. Um, right. So in this, we need a few things. First, get the data path directory here. So that is going to be a string data path directory, and that is going to be a string. Followed by that, we also need a tokenizer, like I said, and that is going to be the auto tokenizer, which we already got. Okay. So here, self dot data paths. Here it is just directly, right? So we are going to do a glob of data path directory plus star star. Here it is under the assumption that you provide the data path directory with the slash. Okay. Um. Next, we need to get the tokenizer. Self dot tokenizer equal to tokenizer. Self dot tokenizer dot pad token will be equal to self dot tokenizer dot us token. Always remember to set this, and then max length. Self dot max length is going to be max length. Okay. So max length is something we need to get here because we need to truncate and pad it to that number, which is by default 256, but we can override it. Okay. Here the important functions, if you remember from our prerequisites video, are length, for which here the data points, there are one data point there is one data point per file, which means len of self dot data parts is more than enough for this. Okay. And in here, in get item, def under get item self comma index, what do we need is, first we need to open the JSON file at that index. Okay, with open self dot data paths of, let's put it as for me, I feel weird of using index. Let me have it as idx. Self dot data paths of idx. It is gonna be in R format as f. Content will be equal to JSON dot load of f. Here, the text, which is our input text, will be content of text. All right. And then we have tokenized inputs will be equal to self dot tokenizer of text, where we'll be giving padding equal to max length. Basically, we'll just pad it to 256 if it is not there. Truncation will be set to true, because if there is a value, I mean, if there is a sequence which is bigger than max length, then that also would be, truncated to 256. And then we'll have max length provided, which will be equal to self dot max length. And then return tensors. This is another parameter which is just to provide the tokenized input as tensors. Okay, and that will be pt. All right. So now tokenized inputs of input IDs will be equal to tokenized inputs of input IDs, because it will consider a batch, but we are not batching it. We are batching it later. So first we'll squeeze it so that the first dimension goes off. Okay. And here the labels and input IDs are the same. Okay. Because basically you're going to finish the same, right? So here, sorry, the labels will keep it the same as input IDs actually. Okay, because basically if you see, we are just predicting the next token, which is to replicate the ground truth, right? So the ground truth, which is the input sentence, is going to be the same here, but inside we'll do something known as shift right, so that it forces to see the next token. Okay. Right now it is going to be input underscore IDs. Okay. And once that is done, your tokenized inputs is ready, which means we can just return that. Okay. Tokenized inputs. So here you can see our data set is ready. A simple but easy to create and a powerful data set. Let's put it that way. So here it is, create train data loader of data path directory, and then we are providing max length, which will be equal to 256, and then we'll provide a batch size. Like now let's consider 1. Okay. And then shuffle It is another parameter. We'll set it to true. Drop last. It is again a parameter for data loader. Let's consider that to be true as well. Basically, what it will do is, if there is batch size 2, it will try to combine the values in the data set, and then it will see like, okay, there is one thing missing, so I'll just drop it, that batch. Okay. So that is what is that. And then num workers, data loader num worker. I don't have a very big computer or GPU or CPU, so to speak, so I'm just keeping it to 1. Okay. I don't have that many threads to work with. So tokenizer will be auto tokenizer dot from pretrain of OpenAI community, if I'm not wrong, slash GPT-2. And then here, first I'll create GPT-2 dataset equal to what? GPT-2 dataset of data path directory, which we already got here. Max length, we already got it here. And then we need, we need the tokenizer. Okay. Tokenizer and then max length. Yeah. So now it looks good. So we need to create a data loader. Um, if you see in pre-training, we don't do a lot of evaluation loops because it will delay the pre-training. Okay. So for that, what we usually do is we take a sample, a checkpoint, and then we'll do evaluation loop on that so that it doesn't disturb the pre-training. So that is how I'm just going to keep here. There is not going to be an evaluation loop. So here for data loader, we are providing the batch size. We are setting the shuffle to true. Drop last. uh, I'm just adapting to this new keyboard. Drop last. Again, it is going to be drop last to true. Num workers is going to be num workers, which is 1. And then here I'm going to return this data loader. And that is how our data loader is going to be ready. All we need to do is now create in the model. There are going to be some changes which we need to do. So for example, I did this one change which is to return the attention weights. Previously I used scale.product attention from torch, right? Instead I use their direct function so that we can return the attention weights for for ourselves to visualize. Okay. So you can see attention weights is also returned in that way. So yeah, that is one change which I did. Now, what I'm going to do is first I'll show you how to create a simple training pipeline, which is not very complicated. It will be around 100 line of code max to max. And then what we'll do is I already created, for one of my pipelines, I already created a very complex, which a training pipeline which has all the capability in it. I'll provide you with that code and I'll show you I've just adapted it for our pre-training. I'll just show you that code. I'll just give you a walkthrough so that you guys will be able to use it. Okay. So let's first create a file. Let's say put it as dummy train.py, because like I said, this is not something which you can use for pre-training directly, but this is how you need to start a training loop. Any training loop you write, it should start from here, because this is going to be the base and you'll be adding functionalities on top of this actually. Okay. So let's see how to create that kind of a training loop first, and then we'll move on. So now let's create the dummy trainer, for which we need to import a few from GPT to config import star, because for this I have kept some config. Here you can see number of epochs, learning rate, batch size, weight decay. All of these are provided there. Those are there. From GPT to data set, will be importing Sorry. Um, Create train data loader, and from GPT to model, I'm importing GPT-2 web model, and here, just so I can access a few functionality by providing typecasting, I'm also importing torch.utils.data import data loader, because when I provide it as init parameter, right, I can access a few functionality here. It will basically give me autocomplete. That's all. Um, from torch.optim, we need an optimizer, right? So I'm going to use AdamW with weight DK. I'm going to use AdamW. Um, import torch.nn as nn. Import torch.nn dot functional as if. These are some common imports. I'm not sure even if we are going to use a few of these. Um, from tqdm import tqdm import torch finally. Okay, so this should be here. Okay, looks good. Now let's try to create the trainer. Okay, sorry about that. um Class GPT-2 trainer, which will have an init function, which will have a model, which will be the GPT-2 web model, which we already created, and train data loader, which will be a data loader. Okay, so these are the two parameters, and here self.model will be equal to model. And now if I highlight the model, right, it will give me the values of, like, the characteristics of GPT-2 web model, which is an nn.module. Okay, so if I call forward and all, it will work basically. Okay, so then we have self.train data loader, which will be equal to train data loader. All right, now time to initialize a few function, which is self.device equal to device, self.learning rate equal to learning rate, self dot number of training epochs, which is equal to number of epochs, then self dot batch size, which is equal to batch size, and then self dot weight dk equal to weight dk. Okay, here I need to import two things. One is a loss function, which is gonna be, if you all remember, nn dot cross entropy loss. Right, I've already told about that and why we need to use this. Please watch the pre-training guide if you haven't watched yet. And for optimizer, we are going to use AdamW, for which you need to provide the parameters which you are going to optimize, which is the model parameter, self.model.parameters. Here you can see, right, the parameters completion is, it is showing for me here. That is why I had those as typecasting. Okay, so not typecasting, type identification, let's put it that way. Self dot learning rate, and then we have weight dk, which is self dot weight dk. Okay, all of these values are provided. Now, what I'm going to do is um, I'm going to create a few functions which will complete. Okay, train one step for which it will have self, and then the input batch it needs to train for, and then train one epoch, which should basically have self alone. And this input batch as well, what we can do is model forward will have a few optimization to get the loss. So let me put it as model int batch, which will take again self comma input batch. Okay, and here also I'm gonna have it as pass. Finally, these are just going hierarchically, right? So finally, def train of self, and that is gonna be starting with this. Okay, first to track the global steps we are gonna calculating, because sometimes if data is very less, we do training for multiple epochs. So to calculate global step, it is very important. So next, epoch losses track. So basically, I need to have a list of loss at each epoch. So that is here, and then epoch losses. Okay. So what happens in epoch losses track and what happens in epoch losses is that in epoch losses track, whatever loss was there in each epoch, that will be there, and in epoch losses, loss at end of each epoch, that will be there. Okay. Now, since it is training, like I said, we might train for multiple epochs. So it will be for epoch in range of self.num epochs. What we'll do is first we'll add a logging here, printf string, where I'm gonna say I'm running epoch number. Okay. Let's put it +1 because it is gonna say 0. It doesn't make any sense. Let's put it that way. And then here, uh, okay, I'm gonna assume that in train one epoch, I'm gonna get a few values which I require. Like I said, the train losses, the steps completed, how many steps completed, so that I can update the global steps. Okay, steps completed count, and then epoch loss. What was the loss at the end of the epoch? Okay, epoch loss will be equal to self dot train one epoch. This is just so you know. Now I'll know what I need to expect in train one epoch. That is why I usually go in this way. So here, epoch losses track, I'll append it with train losses, and then epoch losses, in that I'll append the epoch loss. Okay, so basically, if you plot the graph of epoch loss track, you will get the loss curve. Okay. Next, global step will be updated with steps completed count. Okay. Um, so after this, finally, we can do a few logging. I'll just pause it now, and then I'll just put that logging. Okay. I'll write it because if I'm gonna type it, it'll take a few minutes. Okay, I've typed it. Here you can see. So I'm just basically saying completed epoch number, whatever epoch it is, epoch stats. So this is the train loss at the epoch, and then this is what this step is, the step I've completed right now. Okay. So here you can see the train is done. will go one step below, which is to train one epoch. Here, what we need to do is we need to set the model to train mode. Okay. And then here we need the train losses, right? So basically, this train losses will come from train one step. So basically, whatever loss we get there, we'll just append it to train losses, and also steps done. Steps done equal to -1, so that we can provide the steps done as well. So for input batch, so we are getting the input batch from the train data loader, self dot train data loader. I'm gonna add a TQDM there, okay? Because that is when we'll know, like, how long the training will go actually. Um, Loss equal to self dot train one step of input batch. Okay. So basically, I'm expecting that the loss, I'll get it from train one step. Um, then what I'm going to do is steps done will be equal to um, plus equal to 1, because one step is done here. And then train losses dot append of loss. Here, the epoch loss, which we need to calculate here, will be equal to sum of train losses, whatever losses I have right now, by the steps done. Okay. Um, so I'll return these train losses, steps done, and then epoch loss. Okay. So now you can see in train one step, I'm expecting a loss, right? So here in a training loop, what happens is first we set optimizer to 0 gradient. So that is done. Now next what we need to get is the loss. Okay. So there what I'm going to do is I'm going to call model input batch. Okay. Assuming I get the loss, I need to do loss dot backward. Now you can see it is not highlighting, right? If I did loss is to nn dot cross entropy loss. Oh, still it is not doing, maybe. Okay. Seems like if I don't do a return type, it won't work. That's fine. No, not an issue. Let me keep it that way. So backward propagation starts. Now I need to update the gradient based on that. So for that, self.optimizer.step. All right. So all I need to do is just return the loss. This is what happens in one step of a training. And in one step of the training, what happens is you also do model forward, right? That we'll see here. Okay. Model inputs will be equal to input batch of input IDs. We'll make sure that it is in the device. Okay. Self dot device. Similarly, we need to do it for labels as well, so that loss function doesn't give any issue. Okay. Now these two are done. I need to get the logits, which is the model output. Self dot model of model ints. And here, if you see, like I told here in the model, where is it? Here it is. If I provide return attention weights to true or not, doesn't matter. At least a none will come. Okay. So basically, what we can do is logits, comma, attn weights. So that is going to be self.model of. And then here, we need to do that shift which I said. Shift logits will be equal to logits of batch dimension, whatever it is, doesn't matter. And here, till last, I'll take in the tokens, and the embedding dimension is going to be same. I'm not going to touch it since I'm changing the structure a bit. So I'm just making sure that it is contiguous. And in labels, shift label is equal to log it's off. Again, batch size doesn't matter to me, whatever it is. And then from first token, I'm going to take till the last token so that this forces it to calculate the loss based on the next token. Okay. Now I'll get the loss. Okay. Loss is equal to self dot loss function of shift logits dot view of -1 comma shift logits dot size of -1. Okay. And then shift labels. Oh yeah, I think this is where it is. Shift label dot view. I guess it is view of -1. Okay, so everything will become a single token. Okay, so it will be, if it is something like this, it will become something like a s, like this. Okay, so that is what happens here. um that is when it can compare the tokens, and then it will aggregate a value in state, like this is how it is deviated. So now we have the loss as well. So we are not going to do anything with the labels. I think we did something wrong here. Here it is. I just copied it, but I didn't change it. It's fine. um Attention rates are not going to be used. That is not an issue here. So right now let's test it. Okay, it is around 70 times function. If dunder name is equal to dunder main, first we'll create the model equal to GPT to web model, and here I'm making sure that it is converted to device. Okay, and train data loader will be equal to create train data loader, in which I need to provide the path, which is mini GPT-2 pre-train data slash final JSON data slash, and then it can take all the values from there. If you remember, I told, right, we need to put that slash for must. Trainer will be equal to GPT-2 trainer, for which we need to provide model and train data loader. Both are provided. And if I call trainer dot train, here you can see, actually, if you see, this function doesn't have a save or checkpointing. Nothing is there here. Okay, apparently we didn't use these two imports. That is fine. So let's see if this works. Usually this is how I train, but I might have missed a few here and there. Dummy train, it is giving me some issue. That is warning. That is not an issue here then. Okay, it is showing me 7 minutes. So what I'm gonna do is I'm just gonna leave it here. Okay, I'm just gonna stop it. So because actually it doesn't have any save function at all. So what I'm gonna do is I'm having a function which I already created, a training loop, let's put it that way, which is a realistic training loop. Okay, GPT-2 train.py. I have already created that code. I'm just going to explain that now. Okay, it is a 300 line loop actually. Okay, Oh, it is not 300, it is 400. These are the imports. Logging is to log. This is to provide the type, what it is there. Torch we know, and torch distributed in that we import as dist, because this is how you can do a distributed training. In training, it is not always you can train with a single GPU. In pre-training, you have multiple GPUs, so you need to do strategies like DDP, FSDP. You can use deep speed. For all of those, you need to use a distributed function. Data loader, like I said, there is DDP here, and there is a grad scaler. So basically, this is used to scale the gradients. Okay, sometimes the gradient will go like 400 and all. We need to scale that down. So that is why there is a grad scaler. A tensor board logger, which is summary writer, and then a linear LR scheduler, which is linear rate scheduler, for which there is get linear schedule with warm up. And in Torch distributed FSDP, there is methods like FSDP, and then there is sharding strategy. So basically, what happens in FSDP is your model will be sharded across your GPUs. Unfortunately, I can't show any of these here. This is a function which I generically wrote on an assumption that you guys have a multi GPU. Unfortunately, I don't. Okay, but this code should work. If it doesn't, hey, you can just let me know. I'll try to help you out. Okay. Unless I mean, like, if you have a multi GPU, let's put it that way. In FSDP, again, there is auto wrap policy. This is to wrap the models for FSDP instance for transformers. Okay. Um, there is other imports like NumPy, Seaborn to visualize the attention mask. So to show that there is PyPlot, and then for progress bar there is TQDM and JSON and all. And here you can see this is the default config. Oh, sorry, outputs for output directory, logs for logging directory, number of epochs. Let me put it 1. Learning rate is 5 minus 5. I can also keep it as 2e minus 5. Anything is fine. I'll just keep it for 5e minus 5. Weight decay 0.01. Warm up steps 10 is more than enough. Gradient accumulation steps is 1. So wait, if you don't know what is gradient accumulation steps, gradient accumulation steps is a parameter which will control at how many steps you want to do back propagation. Okay, that is what is gradient accumulation steps. And then max grad norm, like I said, it will clip the gradients to some scaled value. Mixed pressure, I don't want to do it in mixed pressure, which is FP16 or BF16. I don't have that good GPU. Parallel mode, like I said, if you have a good GPU, you can do mixed pressure and parallel mode, which is DDP, FSDP, deep speed. You can enable one of these. Unfortunately, I don't have GPU to do that, so I'm just keeping none. Checkpoint interval, I'm not sure how many checkpoints we have. Like I said, this is a code I have written already for another use case. So I'm just going to adapt those actually. Okay, so let me put it as 100, no, 400 maybe. I'm not sure how many steps we are going to have. And at 400 steps itself, show me an evaluation. At 400 steps, show me an attention visualization. We are going to ask everything from the model. With pre-training, there is a functionality which you need to provide, which is resume from checkpoint. So what and all you need to do in training group, please watch the theory video which I have already made on LLM pre-training. At that time only I created this code actually. So these are some important things which should be there in a pre-training code. Okay, because sometimes your GPU connection might go off, so you need to resume from checkpoint. Let's say it is for 1 month pre-training and you are done with, let's say, 20 days and it is getting stopped. Okay, so at that time what you'll do is you'll start from the 20 days, whatever latest checkpoint you have. So that is resume from checkpoint. Right now it is none because I haven't trained yet. A local rank function to get the local rank. Like I said, if it is multiple GPUs, you'll get a local rank, but I don't have a multiple GPU. Deep speed config is none. FP16 enabled as false, but you can make it true if you set expression to true. Logging steps is 100. At every 100 step, I need to have the loss and all. Okay. So here you can see I'm just getting the configuration, self.setup directories, which will make sure that there is output directory and logging directory so that things can be stored there. Initializing the model, training data loader, evaluation data loader, setup distributed, which will do a distributed setup. Okay. So here you can see, um, first we get the device, and if it is DDP, first you need to distributed.init process group, for which you should use a backend known as an NCCL. If you're using CPU, I think there is a backend known as Glue, if I'm not wrong, I'm not sure. For which you need to provide your device IDs. Like, local rank will say what is the device you are there, and there is a world size. So how many GPUs you have, that is also there. I don't want to install deep speed, so I wrote the code and then I commented it, but this is how you can do. Like, with deep speed, you need to provide the optimizer as well. Okay. Um, for FSDP, first you'll get the mixed precision policy, and then you'll enable it with FSDP, where you need to provide model, your mixed precision policy, and then sharding, like how you want to shard it, your auto wrap policy, and then backward prefetch. Okay, all of these needs to be provided. And if you're doing a simple, a single GPU training, just do model to self the device, and that is more than enough. Okay. Next, it is to set up the training components. For training, you need, um, your optimizer. Like I said, if it is not deep speed, you need an optimizer from here, which is Adam W, and we are making it like before, but we are also making the number of training steps. We are calculating it. So basically, it is going to be length of the training data loader with multiplied with the number of epochs, and the scheduler is going to be provided with the optimizer. So basically, what it will do is it will change the learning rate of the optimizer at some time. Okay, it will have a logic behind. So it is a linear logic here. But yes, it will differ with optimizer. There is cosine, there is linear with warm up. We are using linear with warm up. There is also something known as reduce LR on plateau. So what it will do is when the training loss becomes, not changing a lot, 0.1, 0.11, 0.9, 0.9. In that range, it will try to reduce the learning rate. There are different types of learning rate scheduler, and one of those is this. Okay. And here I'm just saying that the warm up steps, like what it will do is warm up steps till that it will not change the learning rate. And after that, it will start to change the learning rate according to the loss function or loss we get. Okay. So warm up steps is here. Grad scaler, like I said, it is to scale the gradients. And then loss function is a cross entropy loss. Okay. So these are the important things. Other than that, we are having a function to load the checkpoint if you want to resume your training. And we are initializing a TensorBoard logger, which will save it in the logging directory. So for load checkpoint, if you see, we'll load the model, optimizer, scheduler, and which step we want to start. All of these will be obtained from load checkpoint. Okay. And if you see the save checkpoint, it will have all of these information. Okay. Step, model, state dict, optimizer, state dict, scheduler, state dict, loss, config, everything will be there. Okay. So these are the primary things which you need to do. Now let's go to the train. So there are other functions here, but right now let's start with the train function. So you can see there is a logging stating that, we are starting the training. We are getting the global step, setting up a progress bar with TQDM of len of data loader with the number of epochs. And here for epoch in range of number of epochs, we are running up the loop where we are setting up the train model to train function trains mode. Epoch loss is set to 0. We are going through the batches in data loader, and since we put enumerate, it will give step and batch. If not enumerate, it will give the batch directly. Here we are calling the train step. We'll go through the train step later because it is going to be the same, almost same as what it was before in the dummy train as well. So here we are providing the batch and the global step. Along with that, we are just getting the output loss, which we are adding with the epoch loss. Okay. And then here, if you see, we are just seeing, like, when we want to log, and if we want to log, we'll log these metrics, which will be sent to the log metrics function. And here you can see in log metrics, first those values will be added as scalars. Added scalar, it's just a value adding function in TensorBoard. So that is about that. And in model parameters, so here we are just adding a histogram for whatever parameters are there, and for gradient norm we are adding a scalar again. So for visualization attention, once we get the attention map, so here you can see the attention maps are there. So this is just for the evaluation set. Okay. We get the outputs, and we are saying output attention is true, and here we are getting the attentions of layer -1, and we'll just see the attention map. So basically that is about attention map, so to speak. Here right now, consider continuing with the training loop. Let's come to the train step later. Here again we are seeing, like, when we want to evaluate, and if we want to evaluate, we'll evaluate, and then we'll also log those metrics. And also we'll see, like, when we want to save as checkpoint, and if there is a saving required, we'll go to the save checkpoint, and then we'll do save checkpoint as well. And here, once these are done, we'll add the global step one step forward, and then progress bar will be updated. And here you can see epoch loss is calculated by dividing with the help of train total loaded length, and then the logger is there to log. And then we have our metrics here, eval metrics, which is to call the self.evaluate, and that eval metrics, whatever we got, will be logged, and then save checkpoint will save the checkpoints basically. And then once these are done, we'll close the writer, which is the logger. Okay. Okay, looks good. So right now what I'm going to do is I've kept the config at two places, because this is like the default configuration, and if I override this, I can, if I want to override this, I can override it at the bottom. Okay, that is how this is set. So basically I don't want to do that, so I'm just going to keep it like this, config. Okay, now it looks good, and the path is going to be mini gpt to pre-train data slash what is that? I think final JSON data. Final JSON data. Still, the data set is going to be the same data set as before. So that is there. When we call the train function, if you remember, the train step is not seen yet. So if you go to the train step, first we'll see if there is some expression which we need to do. If we need to do, then we'll do an autocast, and then we'll make sure that it works for expression. And if not, the pipeline will go here. Okay, the pipeline other than that remains the same actually. Okay, here you can see model will be there. We'll be sending our batch IDs, and then we'll get the loss function. Once the loss is done, we'll divide it with the gradient accumulation steps, because like I said, you'll accumulate it, right? And how that accumulation happens, here you can see. Okay, if it is equal to 0, at that time only you'll do the back propagation. Like, basically back propagation will happen, so that gradients will be stored actually in the loss itself, and optimizer dot step will then optimize the parameters. That is how gradient accumulation step basically works, and then we'll get the loss function. Okay, and when you go for evaluate, this is the function, outputs comma attention weights. Okay, that is fine. And in visualization attention as well, outputs comma attention weights. Let's put it this way. Hopefully this should work. So yeah, these are the things which are there. So if I call, sorry, Python GPT-2 train.py, it should start the training without an error, hopefully. And also, guys, this same code will execute in Google Colab. If you don't have a local GPU, please don't run it in local. Just take these code, implement in Google Colab. That's all. Simple. Okay, there is 7,000 steps apparently. Okay, people object has no attribute view. Okay, yeah, outputs, comma, attention, waits. I changed it and I didn't change here. That is my mistake. 7,000 steps. I'm not sure when it is going to end. Mm, Okay, it is showing me 8 minutes apparently. So what I'm going to do is I'm just going to leave this like this itself. So, like I'll just make sure that this is made fast. Okay. But here you can see loss is decreasing, right? 8 to 4, it is decreasing. So I'll just leave it like this. Let's see where we end up. At least if it is 1 or 2 at the end, I will be very happy. 3 is also fine by me. Okay. Let's see at the end of um, you know the training probably. And here you can see logs is printed and outputs is saved. Okay. So all are there. So let me see if there is any logs here. There are logs, and here you can see that many checkpoints. So what we can do is tensor board. This is there. Yeah, it is there. Tensor board hyphen log dir this is equal to logs. Um, Let me see if the board has all the logs correctly. So here there is a tensor board. Let me show you right now. So I hope the tensor board is actually visible. Right. So here you can see that the loss it is getting down. Um, Here you can see. So it was something like this, and here you can see the good point is it also shows time actually. Okay, so it started from somewhere 5 and it has gone down. If I smooth it, here you can see. So this looks like a good loss graph. Even if I do training, it will go here and then stop somewhere. Okay. Um. So those are the scalars, and I can see like epoch. We didn't do multiple epochs, so it is going to be a single epoch. Right. As far as the learning rate is concerned, it started from 4.94 e minus 5 and it ended up somewhere at 2 e minus 5. So that was about the learning rate. And the train loss, it is coming up from 6.177 to the final one being around 1 point smoothed 2.269. Yeah. So that is yeah. So that is all about the training laws and all. But what we are going to do is we are going to have another day where I'm just going to show you how you need to understand the evaluation. Okay. So next video will be about the perplexity theory and how you can calculate perplexity and visualize attention weights and then make some inference out of it to understand how basically things work. And here you can see the value is 1.628. That is the loss we ended up with, and that is a good training loss. So next video is about inference and then moving up to different things like that. Okay. I'll see you all in another video. Until then, happy learning. Let's see. During training, a very important step which is usually not given a lot of importance is none other than the evaluation step. Here, I have created a perplexity evaluator where we'll try to evaluate the perplexity of the model. Also, we'll try to understand how our model does attention. Why is this? When you give perplexity, you will understand what or how much the model is confused to see a new data. I'm not expecting a great performance here because we have just trained it with 7,000 samples. That is nothing. But right now, the aim is to understand the working, right? Not to pre train an LLM exactly, so to speak, because I don't have that good resource. Um, so here I have written a code which I'm going to explain you now. This is not needed. So let me start with the evaluation first, and then I'll show you how you can basically calculate the perplexity, how you will visualize the attention, and also as a bonus, we'll see some inferences as well. Okay, all are gonna be there in this video, so stay till the end and have some fun playing with your video, your own model. All right. So as a recap, what we have done till now in day 8 was pre-training LLM, for which I've used GPT dummy train.py, where I have done some updation and all. With those updation will be there in the GitHub. Okay. And then there is also a GPT-2 train.py file, which has all the capabilities, which we have seen in detail in day 8. Now it is day 9 and we are moving on to evaluation, because the training 1 epoch is done and we are at around 7 laws. So I'm expecting a lot of repetition because the training started at 10, if I'm not wrong, and then it ended up at 7. So I'll say the training is working, but it needs more data for it to understand. Okay, let's see how much it is confused right now. So for this, what you need to do is first create a test set. And here I have a test set of 10 samples, and then I've created a class which is perplexity evaluator, in which I'm having 3 parameters. One is model, and then a tokenizer, and then device. All right. And the model is nothing but the model which we have trained already. Tokenizer is the tokenizer we used while we trained, and the device in which I want to perform this evaluation. So I wanted to do it in, let's take that out. I wanted to do this in GPU so that this will be faster, but you can, if you want, you can do it in CPU as well. It will work. All right. All you need to do is just change this code out to CPU. So what we're doing is, first we are getting the model, changing it to device. So basically the model will be initialized in CPU, but we are converting it into GPU, and then we are setting it in evaluate mode. Okay. And then there is a function which is calculate perplexity, which is helper function used in evaluate dataset. So evaluate dataset is a function which will take a list of string as input and will provide perplexities as well as attention weights. Right now, we don't care about attention weights. We'll care about that later, but we care about perplexities right now, and that is what we are going to see. Okay. We go through each of the text and then we calculate the perplexity, and then we are just appending the perplexity. That is what is happening here. So in calculate perplexity, what happens? So before going into that, it is very important that you know what is perplexity. Perplexity is the factor at which the factor basically shows how much your model is confused to see a new input coming up its way. That is what is perplexity. Higher the value, worst it is. So lower the better. And here, if you see, we are having the tokenizer, where we are encoding the text, and then we are returning the tensor as PT. That will give us the tokens, right? Now we are providing this to the model. We are getting the attention weights as well. Here we are calculating the loss function, for which, if you remember in the last video itself, I said we need to do shift logits, and that is what we are doing here. Okay. And if you want to see that, it will be there in GPT-2 dummy train. If I go to the loss, here you can see, right? This is how shift works. This basically forces to next token prediction. Okay. And then here, if you see, it is shift logits dot view of -1 comma shift logits dot size of 1 -1, and then shift labels dot view of -1. Basically, like I said, it will convert it to tokens of tokens. Now you are calculating a cross entropy loss, right? This cross entropy loss basically will be exponentiated. That is what is perplexity. Okay. And we are calculating this for all the text which is available. Okay. So there is another function as well, which is visualize attention weights. So how that happens is, we are getting the attention weights here, right? We'll be sending that in this. All right. In that, what we'll do is, we'll take the 0 of every layer and hit. layer in head which we specify. So for example, right now I'm most interested on knowing about the last layers first head, okay, because last layers first head usually has a lot of information to it. So we are taking those attention weights and then we are basically detaching it from GPU, making it CPU, and then converting it into a NumPy array. We are converting the tokens as tokenizer. By a tokenizer, we are converting it into tokens actually, and then we are decoding it again. Why? Because if you see, it is a sentence, right? So you need to split it via the tokenizer. So we are doing two process. First, encoding it, which will give the number, and then if we decode it, it will give the token label. Okay, that is what is happening here. Now, what I'm doing here is plotting a figure which is a heat map where I want to see the attention with my x-tick labels and y-tick labels. Basically, it is the labels at your x-axis and y-axis as token labels. That is what is there. And CMap is Viridis. Viridis is just a color map. That is why it is CMap. And annotation is true so that it will give the numbers. The numbers is basically the attention focus, okay? And FMT is dot to F. So whatever I have, it will be dot to point to float value, okay? After a decimal point, there will be 2 float value. And then I need it as square, okay? So square is set to true. And why is square set to true? Because since your x and y axis are the same, basically it will give you a square, right? And also here, if you see the x-axis is rotate as a 45 degrees. So basically, instead of writing like this, it will be right like this, okay? That is why. And we are saving that figure as well, okay? So this is the visualization section, basically. And in the main section, first we'll load the torch model, and then we'll create the instance of the model, and then we'll load the static. Okay, in this, the static will be there, and then we are loading it via this load static function. And here is the tokenizer as well. Here we are calling the perplexity evaluator, and then we are creating a test data set. So if we call the create test data set, it will just return this list. Okay, now what we're doing is we are calculating the average perplexity, and then also we are visualizing the attention weights of layer last layers first head. Okay, so now let's see the output. Okay, so I haven't actually tested yet, so I'm testing with you all. It might be unbelievable, but I haven't, just to keep my reactions natural. I'm not expecting a lot out of the model. At least if it gives a perplexity in 3-digit, I'll be very happy, but it gives in 4-digit, that is not very good. Let's come to the perplexity later. First, let's see the attention, right? The is giving the most importance to the, quick is giving the, and quick has a lot more importance actually. Basically, the gives quick gives more importance to the actually, okay, because here you can see query tokens are here, key tokens are here, all right? And here you can see, right, everything is 0 because that is how the mask is. And here if you see, once it goes down the line, right, the first token, which is the, has no value literally, okay? And when it comes to dot, literally no token plays any role except dog, okay, which makes sense. But when it comes to this dog, right, the has played a lot of role, not lazy, because the dog sounds something similar, maybe that reason, I'm not sure. And here you can see there are other examples, okay? Apparently here you can see, right, comma is having no importance here. So yeah, basically it will print the attention head, attention weights for literally every test which we created. Basically there are 10 samples, so 10 there. So here there is another thing which you need to see. The average perplexity is 5044, which is literally doesn't make any sense for me. The perplexity usually lesser is good. At least I was expecting in 3-digit, let's say, or like a 500 or something like that, which would make some sense. I'm not sure what this model has learned, When the loss was 7, I didn't expect a lot of it to learn. But yes, this is not something I expected, but it's fine. We are just getting this started. And if you want to train this as a real model, a full-fledged model, let me know. I'll put some, what can I say, resources, and then I'll take up a GPU, cloud GPU, and then I'll train it probably. Okay, so let me know on that fact. So yeah, now let's go with this inference. So if you want that, right, just hit the like button, and if this video crosses 100 likes, even if you don't say, I'll train it for a full model. Okay. For GPT-2 inference, the model is GPT-2 web model, and the device is CUDA. I'm inferring it in CUDA, and I want 100 tokens. Okay. So basically, I've provided my model, device, max length, and tokenizer. So if you're wondering, this is inference. Okay. The model is set to device, and then it is set to eval mode as well. Now, when we call the generate text function, we are using a greedy search where we'll first encode the prompt or input whatever we have with the help of tokenizer, and then it will be converted into the device in which we are inferencing. Here in this case, it is CUDA. Right now, we are starting from input IDs, right? It's like a completion. So generated sequence start from there, and we are running a try loop where with project or no grad for our underscore in range of max length, which is 100 tokens, which will be generated. All we are doing is we are getting the input IDs, sending it to the model, and once we get the logits, we'll do argmax. Okay, so argmax will say which logits, if you see, has the probability for all the tokens which are possible to be the next token. So for example, after lazy, it could be human, it could be dog, it could be cat, anything. For each of those, probabilities will be there. And here we are getting the argmax, which is the most probable one, and that token is concatenated to the sequence which is there, and then this loop will run again. Okay, unless and until we have a end of sequence token, this loop will run, and finally once the loop breaks, we'll decode it. Okay, so that is what is happening here, if you're wondering. Okay. All right. And here, if you see, it is just GPT-2 inference. I'm just saying the future of artificial intelligence, at least if it says something like first is, these are just net inferences. Okay. Like I didn't write this inference code. This is from Claude AI. I'm just being very honest. Okay. And if I run this, I think I should get an error. Yeah. Output/model.pt. Please give me something. And the world of the most of, okay, it is a future of the artificial intelligence. It's trying to repeat something. Yeah, and I can get from where it is coming. And the world of most of the something like that it is trying to say. So our model is repeating. It's fine. We can train this for longer time. That is there. We can increase the layer, we can increase the hyperparameters, that is all there. But the aim of this series has been to understand how you can train the model, and this is how you train the model. So yeah, I'm happy with what we have started, and I see a good potential here. So yeah, let me know. You try to train your LLM and let me know how it went, and soon we'll see on how you can adapt a model to a different task. Okay, so next video will be about, or the next day, it's gonna be about using this model to train a sentiment classifier. Are you all tired like me in writing lines and lines of code just to pre-train this mini GPT-2? Then this video is for you, because whatever pre-training we have done before, it's replicated here in just 60 lines of code. Yes, you heard it right. In 60 lines of code, everything is replicated, and including the model as well. If I'm going to add the configuration, everything is going to add up to around 100 line of code, and in 100 line of code, you're going to become a master in pre-training LLMs by your own. Let's jump into the video right now. First, we are starting up with installation of the libraries which are required. And here you can see the installations is going on here. Until that goes, let's see the configuration. If you all remember the model which we created, which is mini GPT-2, it is just a smaller version of GPT-2, and that is what is used here. And here, if you see, I'm using the embedding dimension as 512, the max sequence length as 256, number of layers 8, heads 8. The same configuration what was used previously is same used here. Now you might again wonder, okay, where is the feed forward dimension calculation? The good thing is Hugging Face does all the things for us, and all of these are running behind. Okay, so if I give n embed, it will calculate by itself that okay, it needs to be n embed star 4. Okay, and here I also have the training configuration where I'm providing all the parameters which are required for training, and you will not believe it, whatever things I've said in the pre-training guide, you need to implement all of those. All of those are here, and even if you want, you can just add a parameter known as even complex things like DDP, deep speed, everything can be done here. If you want to do deep speed, just do deep speed config and provide your deep speed configuration, as simple as that. And if you want to do resume from checkpoint, just add resume from checkpoint and it will do. That is how Hugging Face is. All right. And if you're wondering about real world, this is how real world works. All right. We use the best ways possible to make our life easier and more focus on architecture. So for example, if you want to do custom model, no issues. Just add your custom model here and just use the same training pipeline and it will work. All right. So that is what is our focus. Okay. Till date, it was more about us understanding, okay, this is how things work, model how it works, how we can create those from scratch. Those are done. Now we are moving on to real world. All right. So these are the configuration which I'm using. Batch size is 20. Learning rate is 2e minus 5. Right now, my training data size is 20,000. Eval data size is 10. Max steps I'm considering to be 1,000. Max steps is usually used in pre-training when, let's say, you have 1 million of samples, but you want to train it for, let's say, 5 lakh. Okay, at that time, you can stop it with the help of max steps. Output directory. What is my output directory? Where I want to save my model. All right. And then report to, where I want to log my, let's say, losses and things like that. All right. And then eval strategy, do I want to do evaluation? Like I said, in pre-training, we don't do evaluation, so that is none. Push to hub is set to true. I want to push my model to the hub so that I can, pull it up again and then use it in local. How many epochs do I want to train? I want to train it for 1 epoch. FP16 is set to true. I want to see my losses at every 10 steps. And there is another thing which you can use, which is save total limit. And that is to limit how many files you want to save. So I'm going to keep it int type and then it is 3. Okay. As simple as that. This is a very extensible framework. You can add any parameters you want. All you want to do is just verify your parameter name from Hugging Face. Okay. And I'm pretty well versed with Hugging Face, so I usually don't go there to see. But once you get the hang of Hugging Face, right, these are going to be very simple. Save total limit. All right. Now my configuration is set, which means I need to move on to the next stage, which is to create the model, right? I don't have a model, but why fear when Hugging Face is here? I'm just calling autoconfig, which will get the configuration from Hugging Face, where I'm saying my base model is GPT-2. All right. I want a GPT-2 configuration where I'm changing some things. Okay. My max position embeddings, I'm changing it to my max sequence length. It's like the tokens, right? It is absolute position embedding, which means if I have 256 token, the nn.embedding should be created for 256 tokens. All right. So that is why max position embeddings is given the max sequence length and the number of layers, the stack of layers. How much do I want? I want 8, right? So 8 is provided. Okay. Number of attention heads, again 8. Type word embeddings is just to a normal parameter. You can just skip true, and then all you need to do is just call auto model for cos LLM, which will have a base configuration. Like if you remember, we provide our configuration from the config.py, right? Imagine this to be the config.py file, and then this is the model file which is already written by somewhere, and then we are just providing our configuration, as simple as that. And then we are getting a tokenizer, setting up the padding token to be EOS token. Okay, model is ready, and then we need to prepare the dataset. Like I said, in real world, you get a lot of dataset from Hugging Face itself, and there is one such dataset, and that is tiny stories. For now, like I thought, okay, let me try to do a use case rather than taking some random samples. I thought, okay, let's create a story writer kind of a model, where what we'll do is we are calling this dataset from Hugging Face. It is already there. You can call any number of dataset you want and then concatenate it. If you want to know the procedure, please see the previous day's video, where I've shown you how to collect dataset and then make it a Hugging Face dataset, store it. Everything is shown here, shown there. You can just see that. Okay. And here in training, I'm just taking up, like only 20,000 samples. There are like 2 lakh samples in there, but I don't want to train it for that much. So I'm just taking the first 20,000. And here, if you see the training data, I'm just mapping. It's like a application, like it will just apply this function, whatever you're writing. This is a lambda function, which is a single line special function in Python. This function will be applied to each row. Okay, so here what it says is, go to each row, take the text column and replace the text column value with this value. Tell me a story, and then continue with the text. Basically, this is given so that, like if I give tell me a story, the model will be able to generate a story. Okay, that is why. That is the use case, by the way. Now, the trainer. I know, like, we had a 300 line trainer, if I'm not wrong. See, like, almost every functionality is there in just how much? Everything are parameters, by the way. 20 lines. A big 20 line, but more efficient. Okay. Here, the batch size, learning rate, the number of epochs I want to train, logging steps. If I want, like simple, for example, I want to add my gradient accumulation steps. Okay. Gradient accumulation steps equal to self.train_config.gradient accumulation steps. Okay. All I need to do is just take this parameter, go here, put it up here, give a type to it, int, and then give a value, let's say 2. Okay. Simple. Your training now has gradient accumulation steps. Easy, right? These parameters are here. Like I said, logging, when I want to stop, which is early stopping, push to hub, which is to push the model to hub, which is not needed usually. If you want, you can save the model. That is fine. All you need to do is just add a line, self.model.save pre-train, and then this one, self.train config.output dir. Simple. Your model is going to be saved. As simple as that. Okay. So my training arguments are provided here. In trainer, we are using SFT trainer from TRL. TRL is a library which is written by Hugging Face. By the way, autoconfig will have the model config. Auto model for causal LLM will have all the model config, codes where loading of weights, everything will happen behind. Tokenizer will be created with the help of auto tokenizer. Training arguments is to provide the arguments to a trainer, which is created here, SFT trainer. Okay. SFT trainer is usually used for instruction tuning, but it's all about the task. You can also create it, you create a pre-training pipeline with the help of SFT trainer. That is what I have done here. Okay. Model arguments, training arguments, the data I want to use. This is the text field, which is the field of, or the column which you want to use for training. That is what is dataset text field, and max sequence length. What is my max length I want to train for, and tokenizer, which is the tokenizer I want to use for tokenizing the values which are there in the text column and provide it to model, train it via this dataset following this training arguments. As simple as that. Okay. Now, if you call the train function, it will train. Once the training is completed, we are pushing the model to the Hugging Face hub so that it is available somewhere. And then we are also saving it to the local. Okay, that is what is this code all about. And if I do, I don't need this pipeline. Okay, if I do this main function, as simple as that, it will be created. Okay, you'll be able to see now. Now it is just trying to do this imports. Usually imports take a bit of time. Now you can see the tokenizers are imported. Data is getting imported here. Already model is imported. Right now the training split is getting created. I think out of all the days in the LLM mastery course, I think this is the most interesting day for me because this is the most easiest day to work with. No, okay. There is not a value like none apparently. Where is the value? See here, as simple as that. Even I get error. Go to here, just put it. No. Okay, done. You see? Simple. Just call it again and then you're done. I told no, right? What is the issue right now? No steps and epoch. I said no, if I'm not wrong. Is it save strategy? No, that's what I've written. This. Is it because I didn't provide a save strategy? Okay, let me do a few things. Okay, and I'm gonna do everything here. Okay, so that you guys will be able to see what I'm doing. I'm just making both of these no. Okay. Right. Seems working. Yeah, easy. That's all. Simple. Right? See yeah, my training has started. The training loss is getting printed now here. All right, which means the training is going on. I'll see you all after the training. Okay, it's just 8 minutes for training. Around how many? 20,000 samples, right? And you can see the consumption is still 6.8. If you want, you can push it. Make it 40, and you'll be able to run it for let's say 4 minutes at max. Okay, I'll just leave it here. Let me see you after training. So as you can see here, now my pre-training is done. Yeah, so the loss is 4.37. That is not in a good space, but I feel better because previously it was 7 point something, which is shit to say the least. So since it is in Hugging Face, right, it is going to make our life easier to do inference. So I'm just going to do an inference by calling from transformers import pipeline. Pipe is going to be equal to pipeline of, I'm doing a text generation, right? So it is going to be text hyphen generation, and my model name is what is it? I even forgot the name actually. Yeah, this is the name. I'll just copy that, put it in here, and then create a pipeline. Simple. Pipe. And what do I need here? What is the format I pre-trained the LLM with? Just copy that and ask it to complete from there. Okay. So tell me a story. Let's put it something like once upon a time there lived a ghost. If you know, you know. He was a big, not for a tree, with his friends, a dog, once upon with a lot of power. It is not making a lot of sense, but for just training 5 minutes, I guess that was a pretty good one. A boy named him, he was a big dog, he got the sun, and it is trying to make something. I'll be very happy as far as my training is concerned, just for 10 minutes. Okay. So yeah, I hope you all like this video, because I think this is the shortest video till date, but most information is concise, provided together. So I hope you all like this video. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. And just so you know, hereafter things are going to be faster because we are moving to Hugging Face, and when we move to Hugging Face, things will go faster automatically. Cheers. One of the very important aspects of pre-training is to build an LLM which is capable enough to adapt to downstream tasks and domain specific tasks. We are going to try to adapt the mini GPT-2 which we pre-trained previously to build a sentiment classifier. So for the people who are not aware about what is sentiment classification, it is just to identify uh, what kind of a sentence it is, like what emotion it is there. Is it a positive emotion or a negative emotion? And for that, here we are going to use IMDb dataset. As far as the import goes, we are importing GPT-2 tokenizer, GPT-2 for sequence classification, trainer, training arguments. All of these are imported. And then from datasets, we are importing load dataset. Evaluate is imported to make sure that we evaluate the model with a metric which is required. Right now here, the metric required is accuracy, right? And then we have NumPy as well, imported as NP. Here it is very simple. First we are loading the dataset IMDb, and then here we need these. Train dataset will be equal to dataset of train.shuffle, and then eval dataset will be equal to dataset of test. All right. So these two will be there. Tokenized training dataset equal to train underscore dataset dot map off, and then the same will be mapped for eval as well. Okay. So these two are there for us to work with. All right. As far as the metric goes, we are using accuracy. It's gonna just do an exact match. The tokenizer, we are using just GPT-2 tokenizer because that is the tokenizer which was used to train the mini GPT-2 tiny stories pre-train model. So that model is initialized, but not as just auto model for causal LM. Here we are using GPT-2 for sequence classification. Basically, what is the difference? Now, please watch me, okay? Let's say this is your final layer, all right? This final layer will have, right now, it will be 50,000 columns or 50,000 rooms, let's say, okay? And usually causal LM, what it will say is like, which room you want to go next. Okay, that is what causal LM task is all about, predicting the next token. Okay, but with sequence classification, it is about saying which class it is. So instead of saying 50,000 rooms, here we'll have a specific number of rooms by ourselves. Okay, so for example, this load data set, if you load and see IMDb data set, there will be two classes. Okay, one is positive and then another one is negative. Positive is 1 and negative is 0. So basically you need to provide just num labels. That's all. Okay, so it will just, instead of having a normal LM head with the final embedding layer being, let's say, for example, 512 cross 50,256, it will have it as 512 cross 2. Okay, that is how the GPT for sequence classification final head is attached to the model. Okay, and you'll see the difference, okay, in the way you load this model and the way you load this model, there will be a difference while initialization, and you will see that. And here you will initialize the pad token ID for tokenizer, and that tokenizer pad token ID will be set to the model stating that no, this is the pad token, something like that. Okay, that information will be provided to the model as well. As far as the tokenization function goes, what we'll do is we'll get the examples, and in that examples is nothing but the batch of rows. Okay, so the batch of rows of text will be taken tokenized, where it will be padded to max length and truncated if it is larger than the max length, which is not larger, longer than the max length, which is 256. Okay, this function is applied on train dataset and eval dataset to become tokenized train data and tokenized eval data. Okay, so here what I'm going to do is eval underscore dataset is equal to eval underscore dataset dot select of I for I in range 100. For validation, I need only 100 samples. Validation actually happens in CPU, so it will delay your training process. Okay, so make sure that you rectify that issue. Tokenized train data and tokenized eval data. Okay, now here I'm loading the metrics, which is accuracy basically. And in accuracy, here if you see a function which is named as compute metrics is created, where eval predictions will be taken as input. And in eval prediction, basically you'll have the logits and labels. So eval prediction basically is a tuple which has two values in it. One is logits and another one is labels. And the logits, if you do argmax, it will say a class, like whether it is a positive or negative, and you will compare that with your predictions and predictions with your labels, and that will say your accuracy, how accurate you are. As far as the training argument goes, like I said, this is a template. This can be adapted for any use case. And here also we are adapting the same. Okay, output directory, evaluation strategy, per device train batch size, eval batch size. Since it is fine tuning, it is always good to do evaluation at some point of times, because with pre-training the loss will not converge a lot, but with fine tuning it will actually. So it is always good to do eval at times. And then number of training epochs is 3, save steps is 500, load based model at end is set to true. So what it will do is, it will have the values of or the metrics of each epoch, and whichever epoch gave the best model, that epoch model will be loaded finally and then will be saved. Okay, so that is what load based model at end is equal to true means, and the metric for that is accuracy. Okay, here push to hub is set to true, so that the model will be pushed to the hub. Report to will be tensor board, where I want to store everything in tensor board. And when you provide a load based model at end equal to true and evaluation strategy as epoch, make sure that your save strategy is also epoch. Now you have your training arguments, you have your model, you have your train data, you have your eval data, everything is there. Tokenizer is there. Your metric you want to evaluate, that is also there. So just initialize the trainer with that, call the train function, and then finally an evaluate function to evaluate your model. And that is what we are doing now. I'll see you all on the other side once the training is completed. So right now the training has started. To keep it short, so what I would like to do is I would like to keep it at 1 epoch and a batch size of 32. And let me see if that is possible. It will do in 5 or 4 minutes. Runtime, restart session, yes. I need to install things. Yes, I didn't do that. Once that is done, I'll run this as well again. So right now you can see the data is loaded, tokenizer is loaded. Seems like model is also getting loaded. Those are good signs. Now tokenization is happening. So right now the training has started and it is showing me 6 minutes. Then I'll see you all after 6 minutes. Right now, if you see, the training looks almost complete, and we have got 77% accuracy, which I think it's fine, I guess. But yeah, I'm happy with what I got here. I didn't train for a long time. The dataset is also not that big. So let's see. Right now, I think it is trying to push to the hub. And the evaluation results says it is around 77% accuracy, and I'm fine with that. As long as I get at least one correct. Yeah, I got this correct and I'm happy with that. When I say sad, it should say label 0. Then only I'll be happy. It said wrong. Not good. Is it giving everything 1? Nah. It gave this label 0. Yes, there is room for improvement. There is a requirement for training for a longer time. But yeah, it looks solid. It looks fine, and I'm happy with my training. I didn't train a long time, the pre-training, and still it was able to get a hang of what is going on. So I'll be very happy with that. So yeah, finally we have pre-trained as well as we um, transfer the knowledge for a downstream task. So yeah, guys, I hope you like this video. If you like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in the next video where we are gonna see about the post pre-training pipeline in detail, followed by which will be more focusing on creating task specific LLMs. Okay, so yeah, that is going to be the aim of the days coming hereafter. And finally, yeah, we are almost done with 10 days. And good news for you all is, hereafter everything will be short videos because that is how the content is going to be hereafter for some time. So yeah, guys, bye.